Hello and welcome back. It's good to have you here again tonight. Maybe you're settling into bed after a long day. Maybe you're curled up on the couch, the light falling gently through your window. Wherever you are, whatever brought you to this moment, I'm glad you're here. Before we begin our journey tonight, I'm curious, how was your day? Really, take a moment to think about it, whether it was wonderful or difficult, peaceful or chaotic. I'd love to hear about it in the comments below. Your days, your experiences, they matter. And while you're down there, if you enjoy these gentle journeys through science, consider subscribing to the channel. It helps me keep creating these quiet spaces where curiosity and rest can coexist. Tonight, we're going somewhere cold, somewhere ancient. We're traveling back to a time when ice ruled the world, when glaciers miles thick reshaped continents, when creatures both familiar and fantastical walked across landscapes that no longer exist. We're exploring the Ice Age, though as you'll discover, we never really left it behind. The Ice Age isn't just history. It's written into every valley, every coastline, every creature that survived to tell the tale, including us. So find a comfortable position. Let your breathing slow. There's nowhere you need to be, nothing you need to do. Just listen and learn, and perhaps drift. Now let's begin. When you think of the Ice Age, you might imagine a single event, a time when the world grew cold, stayed cold, and then warmed up again. But Earth's relationship with ice is far more complex, far older, and far stranger than that simple story suggests. Our planet has experienced at least 5 major ice ages over the past 2.5 billion years. 5 distinct epochs when ice advanced across the continents, when glaciers carved mountains and valleys, when the climate shifted into configurations so different from today that the world would have been almost unrecognizable. Each of these ice ages lasted not thousands of years, but millions, entire eons of cold, punctuated by warmer periods, cycling in patterns driven by forces both cosmic and earthly. The first ice age we know about happened around 2.4 billion years ago, so long ago that life itself was still mostly single-celled, still learning the basics of existence. The most recent ice age, the one we think of when we say the Ice Age, began about 2.6 million years ago. And here's something remarkable. We're technically still in it. We live in what's called an interglacial period, a warm pause between glacial advances. The ice hasn't finished with us yet. It's simply resting. Think about that for a moment. The Ice Age isn't something safely distant, locked away in the past like the age of dinosaurs. It's the world we inhabit. We're living in its warmest breath, its gentlest moment, and perhaps someday, tens of thousands of years from now, the ice will return. Or perhaps it won't. Perhaps we've changed the story. But for now, we exist in this strange space between ice ages, in a warmth that is both temporary and profound, building civilizations on ground that was once buried under miles of frozen water that may one day be buried again. 11,700 years. Say it slowly. Let it settle. That's how long ago the last glacial period ended, how long it's been since vast ice sheets began their final retreat from the northern hemisphere. In human terms, that feels ancient. Hundreds of generations, the span of all recorded history, and thousands of years more. But in geological terms, in the time scale of Earth itself, 11,700 years is almost nothing, a heartbeat, a single frame in a very, very long film. To put this in perspective, The last woolly mammoths walked the earth closer in time to the construction of the Great Pyramid of Giza than the Great Pyramid is to us today. When those mammoths died, the very last populations isolated on remote islands, the Bronze Age was already underway in some parts of the world. Cities existed, writing existed, and yet mammoths still browsed on Arctic vegetation, their curved tusks and shaggy coats remnants of a world that was still, in some places, clinging to the Ice Age. This closeness matters. It means the Ice Age isn't some distant abstraction. It's recent enough that its fingerprints are everywhere, in the shape of valleys, in the distribution of species, in the very soil beneath our feet. The landscapes we think of as eternal, as permanent features of the earth, are actually brand new in geological terms. They're fresh scars left by retreating ice, still so new that the land itself is still adjusting, still rising in places where the weight of glaciers pressed it down. We live on a planet that's still recovering from its most recent encounter with ice. And in a strange way, that makes us children of the Ice Age, too. Everything we've built, everything we are, emerged in the warm breathing space that followed the cold. Imagine if nearly a third of all land on Earth disappeared beneath ice. Not snow that melts in spring, but permanent, year-round ice. Glaciers thousands of feet thick, advancing season after season, year after year, century after century. That's what the planet looked like 20,000 years ago, during what scientists call the last glacial maximum. It was the coldest, most frozen moment of the most recent ice age, when ice sheets reached their greatest extent across the northern hemisphere. 30%, nearly a third of all land vanished under ice. To understand what that means, consider this. Today, ice covers only about 10% of Earth's land surface, mostly locked away in Antarctica and Greenland, far from where most of us live. But during the last glacial maximum, ice stretched across all of Canada, most of the northern United States, all of Scandinavia and northern Europe, much of Russia and Siberia, places that are now home to millions of people: New York, Chicago, Berlin, Moscow, didn't exist in any meaningful sense. They were buried under ice sheets taller than skyscrapers, ice so heavy it pressed the very bedrock downward, reshaping the planet's crust. And this was the world that early humans inhabited. Not in the ice, of course. No one lived under glaciers. But around the edges, in the regions the ice hadn't claimed, humans hunted and gathered and survived in a planet radically colder and drier than the one we know. It's humbling, in a way. We think of ourselves as adaptable, as masters of our environment, but we evolved and matured as a species in a world that doesn't exist anymore. The warm, stable climate we've known for the past 11,700 years, the climate that allowed agriculture, cities, everything we think of as civilization, is an anomaly. The real normal, at least for the past 2 million years, is a world with far more ice than we can easily imagine. And perhaps, someday, if orbital cycles have their way, that normal will return. When ice covers 30% of Earth's land, that ice has to come from somewhere. And it comes from the same place water always comes from, the ocean. During the last glacial maximum, so much water was locked up in glaciers and ice sheets that global sea levels dropped roughly 400 feet compared to where they are today. 400 feet. Picture a 40-story building and imagine the ocean sitting at the bottom floor, with all those stories of exposed land stretching upward to the current sea level. That's how much the ocean fell. What does a 400-foot drop mean for the world? It means coastlines that are now underwater were once dry land, plains and forests and grasslands where waves now roll. The British Isles weren't islands at all. They were connected to continental Europe by a vast plain called Doggerland, where forests grew and rivers flowed, and herds of animals migrated between what we now call separate continents. You could have walked from France to England, across ground where the English Channel now flows. The Bering Strait between Alaska and Russia? Also dry land, a bridge of grass and tundra 1,000 miles wide, connecting Asia and North America. These weren't narrow land bridges either. They were entire countries, entire ecosystems, places that existed for thousands of years with their own climates and wildlife and landscapes. And then, as the ice melted, they drowned. Slowly, over thousands of years, the ocean rose and reclaimed them, foot by foot, generation by generation. People would have noticed, not the day-to-day change, but over lifetimes, over generations, stories would have been passed down about places that no longer existed, about lands lost to the sea. In a sense, those stories about great floods, about worlds lost beneath the waves, they're not entirely myth. They're memory, distorted by time, of real places that really did vanish as the Ice Age ended and the ocean came home. There's something wonderful about the fact that the concept of an ice age is itself relatively young. For most of human history, people looked at the world and saw it as essentially stable, unchanging except for the slow creep of erosion and the occasional catastrophe. Mountains were always mountains, valleys were always valleys, and the strange, massive boulders scattered across European landscapes, sitting incongruously on types of rock they didn't match, sitting in places they had no business being. Those were mysteries without answers. Some thought they were deposited by the biblical flood. Others imagined giants or ancient catastrophes beyond imagining. But it wasn't until 1837 that a German botanist named Carl Friedrich Schimper proposed a radical idea, that these boulders and many other geological oddities could be explained if Europe had once been covered in ice. Not just snow, but vast sheets of glacial ice that could pick up boulders, carry them for miles, and deposit them seemingly at random when the ice finally melted. He called this period an Ice Age, Eiszeit in German, and the term stuck. It's hard to overstate how revolutionary this idea was. It meant the Earth had a history, a deep history of dramatic change, of climates and landscapes that bore no resemblance to the present. It meant the world was far older and stranger than most people imagined. And it opened the door to an entirely new way of looking at the planet, not as a static creation, but as a dynamic, changing system shaped by forces playing out over unimaginable spans of time. Schimper's Ice Age gave us permission to see the Earth as it really is, restless, ancient, and forever in motion. And those boulders scattered across the landscape, they became clues, breadcrumbs left behind by rivers of ice, telling us stories about a world we never saw, but that shaped everything we know. Here's a fact that collapses time in the most delightful way. The last woolly mammoths didn't go extinct at the end of the Ice Age. They survived, isolated and forgotten, on a tiny island called Wrangel Island in the Arctic Ocean north of Siberia, until approximately 4,000 years ago. Let that sink in for a moment. 4,000 years ago. The Great Pyramid of Giza was already over 500 years old. The Bronze Age was well underway, humans were building cities, writing literature, developing mathematics. And on a remote, windswept island, most people didn't even know existed, a small population of mammoths still clung to existence. These weren't the enormous mammoths of the Ice Age mainland, though. Cut off from larger populations and confined to an island with limited resources, they had evolved into something smaller, dwarf mammoths, standing only about 6 feet tall at the shoulder instead of the towering 11 or 12 feet of their ancestors. Island dwarfism, it's called, a common pattern when large animals become isolated on small islands. With less food available and no need to defend against mainland predators or compete with other megafauna, smaller size becomes an advantage. Over generations, the mammoths shrank, and they persisted. For thousands of years after their mainland cousins vanished, this population survived, adapted, endured. What finally killed them off, we don't know for certain. Perhaps inbreeding in such a small, isolated population weakened them. Perhaps climate change finally made the island uninhabitable. Perhaps humans arrived and hunted them. But for millennia, they were there, outliving their kin, outlasting the Ice Age itself, a living remnant of a world that had already passed into memory everywhere else. It's a reminder that extinction isn't always sudden. Sometimes it happens in stages, in pockets, with the last survivors clinging to existence in places so remote that the rest of the world forgets they exist at all. Deep in the Antarctic ice sheet, trapped in frozen time, are tiny bubbles of air. These bubbles aren't special in any obvious way. They're just air, the same mixture of nitrogen and oxygen and carbon dioxide and trace gases that surrounds us right now. But they're also impossibly precious because they're old. Very, very old. Some of the air bubbles in Antarctic ice cores are over 800,000 years old, sealed away when that layer of snow first fell and was gradually compressed into ice, before humans existed, before modern elephants existed, before 8 glacial interglacial cycles came and went. Scientists can drill down through the ice, extracting long cores that represent hundreds of thousands of years of accumulated snowfall, layer upon layer. And when they carefully melt those cores in controlled conditions, they can release those bubbles and analyze the air inside. They can measure the exact concentration of carbon dioxide, of methane, of other gases, and know with precision what the atmosphere was like at that moment in deep time. They can literally breathe the same air that existed before our species evolved. What they found is extraordinary. The bubbles tell a story of climate cycling in regular patterns, of carbon dioxide rising and falling in lockstep with temperature, of a planet breathing in and out across the millennia. They've revealed that the current concentration of carbon dioxide in our atmosphere, over 420 parts per million, is higher than at any point in at least the last 800,000 years, higher than during any of the warm interglacial periods preserved in the ice. The bubbles, in other words, are witnesses. They testify to the deep past, yes, but they also testify to the present, to the ways we've changed the air we all breathe. And they do it with a precision that's almost startling, because unlike most evidence from the past, these bubbles aren't proxies or estimates. They're the actual atmosphere, preserved and waiting to tell its story. Imagine standing in what is now Canada, perhaps near Hudson Bay, perhaps in Quebec, and looking up. Above you, stretching into the sky, is ice. Not a frozen lake or a glacier tucked into a Mountain valley, but a wall of ice rising thousands of feet above your head, so tall that it creates its own weather, so massive that you can't see where it ends. This was the Laurentide ice sheet at its peak during the last glacial maximum. In some places, it was over 2 miles thick, 2 miles of solid ice pressing down on the continent. To put that in perspective, 2 miles is higher than even the tallest skyscrapers. It's enough ice that if you stood at the bottom, the top would be far above the cruising altitude of birds, in air thin and cold enough that you'd struggle to breathe. And this wasn't just a small region. The Laurentide ice sheet covered most of Canada and stretched down into the northern United States, burying everything from coast to coast beneath an unimaginable weight of frozen water. And that weight mattered. Ice is heavy, incredibly heavy when you have miles of it stacked up. And it doesn't just sit on the surface. It presses down, compressing the Earth's crust beneath it, forcing the very bedrock to sink. During the Ice Age, parts of North America were pressed down hundreds of feet, pushed into the semi-molten mantle layer below, like a thumb pressing into soft clay. And when the ice melted, the land began to rise again, slowly rebounding like a cushion regaining its shape. Except the cushion is the Earth's crust, and slowly means it's still rising today, thousands of years later, still recovering from the weight of ice that hasn't existed for over 10,000 years. Hudson Bay is still rising. Scandinavia is still rising. The planet remembers the ice, and it's still adjusting to its absence, 1 millimeter at a time. When you think of Ice Age animals, you probably picture mammoths, maybe saber-toothed cats, perhaps woolly rhinos. But the Ice Age was home to creatures far stranger than you might imagine. And one of the strangest was the giant ground sloth. Forget the small, slow-moving tree sloths of the Amazon rainforest. The ground sloths of the Ice Age were enormous. Some species could reach the size of modern elephants, standing over 12 feet tall when rearing up on their hind legs, weighing several tons, with massive curved claws longer than your hand. And yet, despite their intimidating size and fearsome claws, they were herbivores. Gentle giants, in a sense, though gentle might be the wrong word for an animal that could probably defend itself quite effectively if threatened. Those claws weren't for hunting. They were for stripping branches from trees, for digging up roots, for pulling vegetation within reach. Ground sloths were browsers, moving slowly through Ice Age landscapes, feeding on leaves and shoots and whatever plant matter they could find. Different species lived across the Americas, from Alaska to South America, each adapted to its local environment. Some lived in caves, some lived in open grasslands, and they persisted for millions of years, an evolutionary success story that lasted far longer than our own species has existed so far. But like so many Ice Age megafauna, they went extinct around 11,000 years ago as the glaciers retreated and the climate changed, and perhaps as humans spread across the Americas. Today, all that's left are their bones, their fossilized dung, which tells us what they ate, and their massive trackways preserved in ancient mud, showing us that these improbable creatures really did exist, really did walk the earth, slow and huge and peaceful, in a world that no longer exists. One of the most counterintuitive facts about the Ice Age is this. While much of the northern hemisphere was buried under ice, other parts of the world experienced radically different climates than they do today. sometimes colder and drier, sometimes wetter and more hospitable. The Sahara Desert, that vast expanse of sand and heat that dominates North Africa today, has not always been a desert. During certain periods of the Ice Age, and especially during the warm periods between glaciations, the Sahara was green. Not just a little green, profoundly green. Rivers flowed where now there's only sand. Lakes dotted the landscape, some of them enormous, larger than many modern lakes. Grasslands supported herds of animals. Hippos wallowed in rivers. Crocodiles basked on muddy banks. Humans lived there, hunted there, created art there. Cave paintings deep in what is now barren desert show giraffes, elephants, cattle, people fishing and dancing and living lives in a landscape that would be unrecognizable to anyone who sees the Sahara today. What happened? Climate patterns shifted. The African monsoon, which brings rain to sub-Saharan Africa, extended farther north during warm periods when Earth's orbital tilt and position favored it. And then, as orbital cycles shifted again, the rains moved south, and the Sahara dried out, relatively quickly in geological terms, over just a few thousand years. The Green Sahara became the sand sea we know today. The lakes evaporated, the rivers dried up. The animals and people migrated away or adapted or died. And the desert claimed the land, burying the evidence of what had been there before beneath sand dunes that shift and whisper in the wind, keeping secrets about a past that was green and alive and utterly different from the present. It's a reminder that the world's climates aren't fixed, aren't permanent. They're temporary arrangements, always in flux, always capable of transforming into something we wouldn't recognize. The saber-toothed cat, Smilodon, to give it its proper scientific name, is one of the most iconic predators of the Ice Age, and for good reason. Those fangs, those impossibly long canine teeth that curve down from the upper jaw like twin daggers, are unforgettable. In the largest species, Smilodon populator, those teeth could reach 11 inches in length. 11 inches of tooth protruding from the skull, visible even when the mouth was closed, giving these cats a profile that seems more mythological than real. But here's what's fascinating. Despite their fearsome appearance, those teeth were actually quite fragile. They weren't designed for the kind of bone-crushing, thrashing, violent takedowns that modern big cats employ. Instead, they were precision instruments. The teeth were flattened, blade-like, with serrated edges, more like knives than the conical piercing teeth of lions or tigers. An analysis of fossil skulls shows that Smilodon had an extraordinarily wide gape, able to open its jaws to nearly 120 degrees, far wider than any modern cat. This suggests a very specific hunting strategy. The current thinking is that saber-toothed cats used those fangs for what's called a precision bite, targeting the throat or underbelly of prey, using the serrated edges to slice through soft tissue and cause massive bleeding, rather than trying to crush the windpipe or spine the way modern predators do. The wide gape would allow them to get those long teeth into position without their lower jaw getting in the way. It's elegant, in a brutal sort of way. But it also means that if those teeth broke, if they hit bone wrong, or if the prey struggled at the wrong moment, the cat was in serious trouble. Broken fangs appear surprisingly often in the fossil record, evidence that this hunting strategy, while effective, came with risks. And perhaps that's part of why saber-toothed cats went extinct when the Ice Age ended and their prey disappeared. They were specialists, perfectly adapted to a specific type of hunting, and when the world changed, they couldn't adapt quickly enough. We think of ice as static, frozen, solid. And on a human timescale, it certainly seems that way. But glaciers are not static. They flow. They move like rivers, except instead of water, it's ice. And instead of flowing in hours or days, the movement happens over months and years. But the motion is real, measurable, constant. Glaciers are always flowing, always advancing or retreating, always in motion even when they appear perfectly still. How can solid ice flow? The answer lies in pressure and time. When snow accumulates year after year, it compresses into ice. First into a granular form called firn, then into solid glacial ice. As more snow falls and more weight builds up, the ice at the bottom of the glacier is under enormous pressure. And under that pressure, ice doesn't behave quite like the ice in your freezer. It becomes plastic, able to deform and flow, moving in response to gravity and the weight of ice above it. The ice crystals slide past each other, reorient themselves, flow around obstacles. It's a process called creep, and it happens at different rates depending on the temperature, the thickness of the glacier, and the slope of the land beneath. Some glaciers move just inches per year, barely perceptible even with careful measurement. Others can move several feet per day, especially in steep mountain valleys where gravity pulls strongly, or in areas where the base of the glacier is wet and lubricated by meltwater. And when a glacier moves, it carries everything with it: rocks embedded in the ice, sediment frozen into the base, boulders plucked from the bedrock. The glacier becomes a conveyor belt of geological debris, slowly transporting material from where it was picked up to wherever the ice eventually melts and deposits it. And within the ice itself, the layers record the journey, each year's snowfall compressed into a distinct band, creating a timeline that can be read like tree rings, telling the story of the glacier's life from its birth high in the mountains to its eventual melting at lower elevations or at the sea. When we talk about the Bering Land Bridge, the name itself is a bit misleading. It conjures images of a narrow strip of land, a precarious crossing between two continents, something you might walk across in a day or two. But that's not what Beringia was. At its maximum extent during the last glacial maximum, when sea levels had dropped 400 feet and exposed the seafloor between Siberia and Alaska, the land bridge was about 1,000 miles wide from north to south. 1,000 miles. That's not a bridge. That's a subcontinent. Beringia was a vast landscape with its own climate, its own ecosystems, its own populations of plants and animals. It had rivers and hills, grasslands and tundra, possibly even forests in sheltered valleys. Mammoths grazed there. Bison roamed in herds. Humans lived there, not crossing quickly on their way from Asia to the Americas, but settling, adapting, spending generations, perhaps thousands of years, in this land between continents. Archaeological evidence suggests that people may have lived in Beringia for a long time before eventually moving south into the Americas, waiting perhaps for ice sheets blocking the southern routes to retreat enough to allow passage. And then, as the ice age ended and the glaciers melted and sea levels rose, Beringia drowned. Slowly at first, then more rapidly, the ocean reclaimed the land. Coastlines retreated. Rivers became estuaries. Grasslands became seafloor. The people and animals who lived there would have moved, migrating east or west to higher ground. watching as the land they knew disappeared beneath the waves. Today, Beringia is gone, submerged beneath the shallow waters of the Bering Strait and the Chukchi Sea. But it existed. It was real. And for thousands of years, it was one of the most important crossroads in human history. The place where populations from Asia encountered a new world, where the peopling of the Americas began, where Ice Age hunters first looked out over landscapes that stretched, unknown and endless, toward the south. Evolution sometimes takes unexpected turns, and the cave bear is a perfect example. These were enormous animals, some of the largest bears that ever lived, capable of reaching over 1,000 pounds, comparable in size to the largest modern polar bears or grizzlies. And like all bears, they had impressive teeth, including large canines that look to our eyes like the teeth of a predator, an animal built for eating meat. But analysis of cave bear teeth, bones, and the isotopic signature of their remains tells a different story. These bears were primarily vegetarian. Not exclusively. Bears are opportunistic, and cave bears probably ate meat when they could get it, scavenged carcasses, maybe even hunted on occasion. But the bulk of their diet was plants. They browsed on vegetation, ate roots and berries and whatever plant matter they could find in the Ice Age landscapes of Europe. Their molars show wear patterns consistent with grinding plant material, not shearing meat. Their massive size wasn't fueled by hunting, but by the patient, constant consumption of vegetation, the way modern herbivores like elephants or rhinos build their bulk, and they hibernated deeply for months at a time in the caves that gave them their name. In fact, some caves in Europe contain the bones of hundreds of cave bears, accumulated over thousands of years as generation after generation returned to the same caverns to sleep through the worst of the Ice Age winters. These weren't random deaths. These were hibernation sites, and the bears that died there often died in their sleep, perhaps from starvation when they hadn't built up enough fat reserves to last the winter, perhaps from illness or old age or the simple vulnerability of deep hibernation. The result is an extraordinary fossil record, caves packed with bear bones, a testament to how central these refuges were to cave bear survival. Until, of course, they went extinct around 24,000 years ago, victims of climate change and habitat loss, and possibly competition with humans for the very caves they needed to survive. Here's something that seems almost absurd. The difference between an ice age and an interglacial warm period, the difference between mile-thick ice sheets covering half of North America and the relatively warm, stable climate we enjoy today, comes down to tiny variations in Earth's position and orientation as it orbits the sun. We're not talking about the Earth moving dramatically closer or farther from the sun. We're talking about changes in orbital eccentricity, in axial tilt, in the precession of the equinoxes. Subtle geometric shifts that play out over tens of thousands of years. These are the Milankovitch cycles, named after Serbian scientist Milutin Milankovic, who worked out the mathematics in the early 20th century. There are three main cycles. First, Earth's orbit around the sun isn't a perfect circle. It's an ellipse, and the shape of that ellipse changes over about 100,000 years, sometimes more circular, sometimes more elongated. Second, the tilt of Earth's axis, currently about 23.5 degrees, varies between 22.1 and 24.5 degrees over a 41,000-year cycle. More tilt means more extreme seasons. Less tilt means milder seasons. Third, Earth wobbles as it spins like a top winding down, and this wobble means that the direction the axis points changes over a 23,000-year cycle. Currently, Earth is closest to the Sun during Northern Hemisphere winter, which moderates seasons. In about 11,000 years, we'll be closest to the Sun during Northern summer, making northern summers hotter and winters colder. These cycles interact in complex ways, sometimes reinforcing each other, sometimes canceling out. But the net effect is to change how much sunlight reaches different latitudes during different seasons, and especially how much reaches high northern latitudes during summer. And that matters enormously. Ice ages don't start because the planet gets uniformly colder. They start because summer in the far north gets just cool enough that not all of the previous winter's snow melts. Snow accumulates. It reflects more sunlight, cooling the region further. More snow falls the next winter. More survives the next summer. Over thousands of years, snowfields become glaciers, glaciers become ice sheets, and the ice advances, all triggered by a shift of a degree or two in tilt, by a slightly different orbit, by changes so subtle you'd never notice them in a human lifetime. But given time, geological time, they remake the world. Antarctica is easy to forget about. It's remote, inhospitable, mostly empty of humans except for research stations. It doesn't feature much in daily life unless you're a climate scientist or a penguin. But Antarctica matters enormously to the rest of the planet for one simple reason. It contains the vast majority of Earth's fresh water. About 70% of it locked up in ice, sitting on bedrock at the bottom of the world. If you gathered all the rivers, all the lakes, all the groundwater, all the ice in glaciers everywhere else in the world, and combined it, it would still be less than the ice sitting on Antarctica. That ice is thick, unimaginably thick. The Antarctic ice sheet averages about a mile deep, and in places it's nearly 3 miles thick. Enough ice that if you stood at the bottom on bedrock and looked up, the surface would be higher than the cruising altitude of commercial jets. The weight of all that ice is so enormous that it's pressing the entire continent down, pushing bedrock below sea level in many places. If the ice were removed, if it could somehow be lifted away, the land would slowly rise, rebounding upward over thousands of years. And if that ice melted, if all of it, or even most of it, found its way into the ocean, sea levels would rise by nearly 200 feet. Every coastal city on Earth would be underwater. Entire countries would vanish. The map of the world would be completely redrawn. It's a scenario that keeps climate scientists awake at night, though it's worth noting that completely melting Antarctica would take an enormous amount of warming sustained over a very long time. We're talking thousands of years, not decades or even centuries, but the ice is vulnerable at the edges where it meets the ocean, and there's evidence that parts of the Antarctic ice sheet are already starting to destabilize, to lose mass faster than snow can replace it. The ice age may not be over. The ice may be retreating still, slowly, in response to a warming world. And Antarctica, silent and remote as it is, holds the key to what the coastlines of the future will look like. It's hard to imagine hippos in England. The British Isles today are temperate, often rainy, occasionally cold, not the kind of place you'd expect to find animals we associate with Africa. But during the Ice Age, Britain's climate fluctuated wildly, cycling between frigid glacial conditions and warmer interglacial periods. And during those warmer periods, the fossil record tells us something surprising. Hippos lived in Britain. Hippopotamus amphibius, the same species that lives in Africa today, wallowed in British rivers during warm intervals around 125,000 years ago. These weren't isolated oddities either. The Thames River Valley has yielded bones from an astonishing array of Ice Age animals: straight-tusked elephants, rhinos, cave lions, spotted hyenas, aurochs, and yes, hippos. During the warmest periods, Britain's climate was actually somewhat warmer than it is today, almost subtropical in summer, and the landscape supported a fauna that would have looked more at home on the African savanna than in modern London. Rivers teemed with fish, grasslands supported massive herbivores, and predators, including huge cave lions and clans of scavenging hyenas, competed for prey. And then the climate would shift. Temperatures would drop. The warm adapted species would migrate south or go extinct locally. Ice would advance from the north, and Britain would transform into a cold, wind-scoured landscape populated by woolly mammoths, woolly rhinos, reindeer, animals built for the cold. And then, eventually, the climate would warm again, and the cycle would repeat. What we see as normal, the current temperate climate of Britain, is actually just one point in this vast cycle. One moment in a history that has seen the landscape swing between extremes over and over again. The hippo bones buried beneath London are evidence of that. Strange proof that normal is temporary, and that the Earth's climate is always, always in flux. If you've ever seen a glacier up close, or photographs of glacial ice, you've probably noticed something striking. The ice is blue, not white like snow or the ice in your freezer, but a deep, pure blue, the color of a summer sky or tropical ocean. This blue isn't from impurities or minerals. It's intrinsic to the ice itself, a consequence of how light interacts with ice that has been compressed for centuries or millennia under its own weight. Here's what happens. Fresh snow is white because it's full of tiny air pockets and irregular surfaces that scatter all wavelengths of light equally. But as snow gets buried and compressed as it transforms, first into firn and then into glacial ice, those air pockets are squeezed out. The ice crystals become more uniform, more densely packed. And when light enters this dense ice, something interesting happens. The ice absorbs the red and yellow wavelengths of light, but it allows blue light to scatter and reflect back out. The denser the ice, the more pronounced this effect becomes. Ancient ice, compressed for hundreds of thousands of years, appears an almost impossibly vivid blue. This ice is incredibly old. Some of it fell as snow before humans existed, before Neanderthals existed, before any member of our genus walked the earth. It's been compressed not just by the weight of more recent snow, but by millennia of accumulation, squeezed into a form denser than most rock, so pure and clear that you can sometimes see through it like glass. When glaciers calve, when chunks of ice break off into the ocean, you'll sometimes see this ancient blue ice exposed in the newly broken face, glowing in the sunlight like a window into deep time. It's one of the most beautiful things nature creates, and it's also a reminder of the immense age and power of ice, of the fact that glaciers are not just frozen water, but geological forces, archives of climate and time, beautiful and strange and impossibly old. The end of the Ice Age wasn't smooth or predictable. The world didn't simply warm up gradually and stay warm. About 12,800 years ago, After several thousand years of warming, something strange happened. The planet abruptly plunged back into near glacial conditions. Temperatures in the northern hemisphere dropped sharply. Glaciers that had been retreating began advancing again. Ice Age conditions returned, not everywhere, but across much of Europe and North America. And this cold snap lasted for about 200 years before ending just as abruptly as it had begun. We call this period the Younger Dryas, named after a small Arctic flower called Dryas octopetala, whose pollen appears in sediment layers from this time, indicating cold, tundra-like conditions. What caused it? The most widely accepted explanation involves the catastrophic drainage of Glacial Lake Agassiz, an enormous lake in North America formed by meltwater from retreating ice sheets. The lake was dammed by ice, but as the ice retreated, a breach formed, and an unimaginable volume of fresh water, possibly as much as all the water in all the Great Lakes combined, suddenly poured into the North Atlantic Ocean. This flood of cold, fresh water disrupted the Atlantic meridional overturning circulation, the system of ocean currents that includes the Gulf Stream, and brings warm water northward. When this circulation weakened or shut down, the climate across the northern hemisphere cooled dramatically. For over 1,000 years, the world hovered in this twilight state, not fully in an ice age, but far colder than today. And then around 11,700 years ago, the Younger Dryas ended. Temperatures shot up again, possibly within just a few decades. The transition was so abrupt that some researchers think the warming happened in as little as 10 years. A climate shift so rapid that people alive at the time would have noticed dramatic changes within their own lifetimes. The Ice Age was over. The Holocene, our current warm, stable period, had begun. But the Younger Dryas is a reminder that climate doesn't always change slowly, that the Earth's systems can sometimes flip from one state to another with startling speed, and that the warm stability we've enjoyed for the past 11,000 years is not guaranteed to last forever. Neanderthals often get a bad rap in popular culture, portrayed as brutish, primitive, evolutionary, dead ends. But the truth is far more interesting. Neanderthals were superbly adapted to Ice Age Europe, and they thrived in conditions that would challenge even modern humans equipped with advanced technology. Their bodies show clear adaptations to cold climates. They were stockier than modern humans, with shorter limbs and wider torsos, a body plan that minimizes surface area relative to volume, and thus reduces heat loss. Bergmann's rule and Allen's rule, principles from ecology, predict exactly this pattern in cold-adapted populations, and Neanderthals fit the predictions perfectly. But the adaptations went deeper than just body shape. Their nasal passages were shaped differently from ours, larger, with more internal surface area. Why? To warm and humidify cold air before it reached the lungs. Breathing frigid air directly into your lungs is dangerous, potentially causing tissue damage and increasing the risk of respiratory infections. Neanderthal noses were built-in air conditioners, warming each breath before it went deep into the respiratory system. It's a feature modern humans from tropical origins don't possess to the same degree, and it would have been a significant advantage in Ice Age winters. Neanderthals also had brains as large as or larger than modern humans, made sophisticated stone tools, used fire, buried their dead, possibly created art, and almost certainly had language. They weren't evolutionary failures. They survived in Europe and Western Asia for over 300,000 years, far longer than our own subspecies, Homo sapiens, has existed so far. They endured multiple glacial interglacial cycles, adapting to dramatic climate swings, living through some of the coldest periods of the Ice Age. And they only went extinct around 40,000 years ago, possibly due to competition with modern humans, possibly due to climate change, possibly due to some combination of factors we still don't fully understand. But for hundreds of thousands of years, they were the dominant human species in Ice Age Europe, masters of a frozen world, and in their own way, they were perfectly successful. The Ice Age was their world. They were built for it. When we picture horses, we tend to imagine the tall, powerful animals we're familiar with. Today, domesticated horses bred for size and strength, standing 5 or 6 feet at the shoulder, sometimes taller. But Ice Age horses were different. They were smaller, stockier, standing only about 4 feet tall at the shoulder, roughly the size of a modern pony. These weren't the sleek race horses or massive draft horses of today. They were compact, sturdy animals built for survival in harsh climates. These horses lived across vast territories, from Spain all the way to Siberia and into North America, roaming the cold grasslands and steppes in enormous herds. Cave paintings from Ice Age Europe show them in vivid detail. Small, thick-bodied horses with short legs and upright manes, sometimes depicted in groups, sometimes alone. The artists who painted them knew these animals intimately, had watched them graze and run and interact, and rendered them with a precision that still impresses today. What happened to these Ice Age horses? In North America, they went extinct around 11,000 years ago, along with most other megafauna. In Europe and Asia, they persisted longer, and some populations eventually gave rise to the domesticated horses we know today. But the wild Ice Age horses of the steppes, animals like Equus ferus, are mostly gone now, replaced by their domesticated descendants, and by changing landscapes that no longer support the vast herds that once thundered across frozen grasslands under pale Ice Age skies. Woolly mammoths get most of the attention when we talk about Ice Age elephants, and for good reason. They're iconic, well-preserved, familiar from countless books and films. But they weren't the largest mammoths. That distinction belongs to the steppe mammoth, Mammuthus trogontheri, an earlier species that roamed Europe and Asia before the woolly mammoth's time. Steppe mammoths were absolutely enormous, standing up to 15 feet tall at the shoulder and weighing as much as 10 tons, considerably larger than woolly mammoths, and rivaling the largest elephants that have ever lived. These giants lived during the Middle Pleistocene, between about 1.5 million and 200,000 years ago, during earlier phases of the Ice Age. They weren't as heavily adapted to extreme cold as their woolly descendants. They had less hair, lived in somewhat warmer conditions, and occupied a different ecological niche. But they were successful for over 1 million years, spreading across the vast grasslands and open woodlands of Ice Age Eurasia. Eventually, they gave rise to the woolly mammoth through evolution, with populations adapting to increasingly cold conditions by growing thicker coats, developing smaller ears and tails to reduce heat loss, and becoming somewhat smaller in body size. Adaptations that made them better suited to the harsh glacial climates of the late Pleistocene. But for a time, the steppe mammoth was the largest land animal on the planet. a creature of almost unimaginable size, moving in herds across landscapes that stretched from Britain to China. If you could watch the Earth from space across the past million years, watching at high speed so millennia passed in seconds, you'd see a pattern emerge. Ice would advance from the poles, spreading across the northern continents, covering Canada and Scandinavia and Siberia in white. The ice would grow for tens of thousands of years, reaching its maximum extent, holding there for a while. And then it would retreat relatively quickly, melting back toward the poles over just a few thousand years. The world would warm, forests would spread, and then after perhaps 10,000 years of warmth, the ice would begin advancing again. The cycle would repeat. This is the pattern of glacial and interglacial periods, and it's been remarkably consistent for the past million years. Roughly every 100,000 years, the Earth completes one full cycle. About 90,000 years of glacial conditions punctuated by 10,000 to 15,000 years of interglacial warmth. We're currently in one of those warm periods, the Holocene interglacial, which began about 11,700 years ago. By the typical pattern, we're approaching the end of our warm period, though human-caused climate change has complicated this picture enormously. What drives this 100,000-year cycle? It's linked to Milankovitch cycles, particularly changes in the eccentricity of Earth's orbit. But there's still debate about the exact mechanisms, because the orbital forcing at 100,000 years is actually quite weak. Something about Earth's climate system amplifies this signal, turning subtle orbital variations into massive ice ages. Perhaps it's carbon dioxide feedbacks, or changes in ocean circulation, or the dynamics of ice sheets themselves. We don't have all the answers yet, but the pattern is clear in the geological record. For 1 million years, the Earth has been breathing in and out, freezing and thawing, dancing to rhythms set by orbital mechanics and amplified by its own internal processes. Names can be misleading, and Irish elk is a perfect example. Despite the name, this animal wasn't an elk at all. It was actually a type of giant deer, more closely related to modern fallow deer than to elk or moose. And it wasn't exclusively Irish either. Irish elk, more properly called Megaloceros giganteus, lived across Europe and Asia, from Ireland to Siberia, inhabiting the grasslands and open woodlands of Ice Age Eurasia. But it got its common name because many well-preserved specimens have been found in Irish peat bogs, where the acidic, oxygen-poor conditions prevented decay and preserved bones beautifully. What made this deer extraordinary were its antlers, the largest antlers of any deer that has ever lived, spanning up to 12 feet from tip to tip and weighing around 90 pounds. 90 pounds. That's more than many adult humans weigh, and these deer were carrying that weight on their heads, growing a new set every single year, like all deer do, shedding them in winter and regrowing them in spring. The metabolic cost must have been enormous. Growing that much bone in a few months requires massive amounts of calcium and energy. Why such huge antlers? Sexual selection, most likely. Males with larger, more impressive antlers would have been more successful at attracting mates and intimidating rivals. The antlers became caught in an evolutionary arms race, growing larger generation after generation until they reached truly spectacular proportions. But those antlers may also have contributed to the species' extinction around 11,000 years ago. As forests expanded after the Ice Age ended, the open landscapes Irish elk preferred began disappearing, and navigating through dense woodland with 12-foot antlers would have been difficult if not impossible. Climate change, habitat loss, and perhaps those magnificent, impractical antlers all played a role in ending the reign of the largest deer that ever lived. Beneath the surface in Arctic regions, hidden from sight but profoundly important, is permafrost, ground that remains frozen year-round, sometimes for thousands or even millions of years. During the Ice Age, permafrost extended much farther south than it does today, covering vast territories in Europe, Asia, and North America. Even areas well beyond the ice sheets themselves were underlain by permanently frozen ground, creating unique ecosystems and landscapes. Permafrost isn't just frozen dirt, it's a complex matrix of soil, rock, ice, and often organic material, the preserved remains of plants and animals that died and were frozen before they could fully decompose. In some places, permafrost can be hundreds or even thousands of feet thick, with only the top few feet thawing during summer. And because it's been frozen for so long, it can preserve things with extraordinary fidelity. Mammoth carcasses have been found in Siberian permafrost with their flesh, fur, and even stomach contents intact, frozen so quickly and kept so cold that they're barely decomposed after tens of thousands of years. Today, permafrost still covers about 24% of land in the Northern Hemisphere, mostly in Alaska, Canada, Siberia, and Greenland. But it's thawing. As the climate warms, permafrost that has been frozen for millennia is beginning to melt, releasing methane and carbon dioxide that had been locked away, potentially accelerating climate change in a feedback loop. Ancient organic matter, frozen since the Ice Age, is decomposing for the first time, returning its carbon to the atmosphere. And in some places, the thawing permafrost is collapsing, creating sinkholes and unstable ground, evidence that even this permanent feature of Ice Age landscapes isn't permanent after all. The Earth is still changing, still responding to the end of the Ice Age, still in transition. The Amazon rainforest seems eternal, primordial, a vast green expanse that has existed unchanged since time immemorial. But that perception isn't quite accurate. During the coldest, driest periods of the Ice Age, the Amazon was dramatically different. The climate was cooler and much drier, and the rainforest couldn't maintain itself across its current range. Instead, it fragmented, shrinking back to isolated pockets of favorable habitat called refugia, small areas where enough rainfall persisted to support forest, surrounded by much larger areas that became savanna or dry woodland. This has profound implications for biodiversity. When the rainforest fragmented, populations of plants and animals became isolated in different refugia, separated by hundreds of miles of unsuitable habitat. Over thousands of years, these isolated populations evolved independently, adapting to their local conditions, accumulating genetic differences. New species formed. And then when the climate warmed again and rainfall increased, the rainforest expanded, reconnecting those refugia. Species that had evolved in isolation suddenly came back into contact, sometimes competing, sometimes hybridizing, creating the extraordinary biodiversity we see in the Amazon today. The refugia hypothesis helps explain why the Amazon is so incredibly diverse, why there are so many closely related but distinct species, why biodiversity hotspots exist in certain regions. These hotspots correspond to the locations of Ice Age refugia, places where forests persisted through the dry periods and served as reservoirs of diversity that later recolonized the expanding rainforest. The Amazon we see today is, in a sense, still recovering from the Ice Age, still reorganizing after climate changes that ended thousands of years ago, still a work in progress rather than a static, unchanging wilderness. If you know dire wolves from fantasy literature or television, you might be surprised to learn they were real, very real. Canis dirus, the dire wolf, was one of the most common large predators in Ice Age North and South America. Hundreds of specimens have been found, particularly in the La Brea tar pits in Los Angeles, where dire wolves were drawn to trapped prey and became trapped themselves in asphalt seeps, their bones preserved in remarkable numbers. Dire wolves were larger and more heavily built than modern gray wolves, with more robust skulls, stronger jaws, and bone-crushing teeth adapted for a different hunting strategy. Where modern wolves are cursorial hunters, built for running long distances and wearing down prey, dire wolves were likely more ambush-oriented, relying on power rather than endurance. Their teeth show wear patterns, suggesting they frequently crunch through bone, possibly scavenging more often than modern wolves or hunting different types of prey. They ranged from Canada to South America, adapting to various habitats from grasslands to forests. But like so many Ice Age predators, they went extinct around 11,000 years ago, likely because the large prey species they depended on were disappearing as the Ice Age ended. The last dire wolves starved or failed to reproduce successfully, and the species vanished, leaving only bones and the name that would, thousands of years later, be borrowed for fictional creatures. But the real dire wolves were impressive enough without embellishment. Powerful predators that dominated Ice Age ecosystems for hundreds of thousands of years, before climate change and ecological collapse brought their reign to an end. Imagine a lake forming in a valley, held back by a wall of ice instead of rock or earth. The lake grows larger, deeper, filling the valley until it contains more water than some of the Great Lakes. And then the ice dam fails. All at once, catastrophically, the lake drains, releasing an unimaginable volume of water in a flood so massive it defies comprehension. This happened repeatedly during the last Ice Age in what is now Montana and Washington. Lake Missoula formed when a lobe of the Cordilleran ice sheet advanced and blocked the Clark Fork River, creating a natural dam. Behind this dam, water accumulated, forming a lake up to 2,000 feet deep, covering thousands of square miles. But ice dams are unstable. Eventually, perhaps when the lake rose high enough, perhaps when the ice thinned or cracked, the dam would fail. And when it did, the lake would drain in as little as 48 hours, releasing water at a rate that may have exceeded the flow of all current rivers on Earth combined, briefly making it the largest river discharge in Earth's history. These floods carved the channeled scablands of eastern Washington, a landscape so bizarre and otherworldly that it puzzled geologists for decades. Giant ripple marks, dry waterfalls hundreds of feet tall, massive boulders transported miles from their source, all evidence of floods operating at scales we rarely see on Earth. And this didn't happen just once. Evidence suggests it happened at least 40 times, maybe more, as the ice dam would reform and the cycle would repeat. Each flood reshaped the landscape, carving deeper channels, moving more rock, creating a terrain that still looks alien and catastrophic thousands of years later. Air, invisible and taken for granted, has a composition that matters enormously to climate, and during ice ages, that composition was different from today. Ice cores from Antarctica have allowed scientists to measure the concentration of carbon dioxide in ancient atmospheres with remarkable precision, and the results reveal a consistent pattern. During glacial periods, the cold phases of ice ages, atmospheric CO2 dropped to about 180 parts per million. During warm interglacial periods, it rose to about 280 parts per million. This cycle repeated over and over, CO2 and temperature rising and falling together in lockstep across hundreds of thousands of years. Why does CO2 change? It's connected to ocean chemistry, biological productivity, and the carbon cycle. When the climate cools, cold ocean water absorbs more CO2 from the atmosphere. Changes in ocean circulation affect how much CO2 is stored in the deep ocean versus released to the air. Changes in vegetation, less forest, more grassland during ice ages, affect how much carbon is stored on land. All these factors interact in complex ways, and the result is that CO2 naturally fluctuates within a range of about 180 to 280 ppm. Today, atmospheric CO2 is over 420 parts per million. That's higher than at any point in at least the last 800,000 years, higher than any interglacial warm period preserved in the ice core record. We've pushed the atmosphere outside the range it's naturally varied within for nearly 1 million years, and we did it in less than 2 centuries. The ice cores give us context, a baseline against which to measure the present. And the message is clear. What's happening now is extraordinary, unprecedented in the long history of ice ages and warm periods that ice cores preserve. The largest predator in Ice Age North America wasn't a saber-toothed cat or a dire wolf. It was a bear, but not like any bear alive today. The giant short-faced bear, Arctodus simus, was enormous, standing up to 11 feet tall when rearing up on its hind legs and weighing possibly up to 2,000 pounds. Even on all fours, it stood taller at the shoulder than a modern grizzly. And unlike most bears, which are omnivorous, the short-faced bear appears to have been primarily carnivorous, a true predator. Its skeleton shows adaptations for a predatory lifestyle that modern bears don't possess. It had long legs relative to its body size, legs built for running rather than climbing or digging. Its face was shortened, hence the name, with powerful jaws, but a skull shape that suggests it wasn't crunching through heavy bones the way some predators do. Some researchers think it might have been a pursuit predator, capable of running down prey across open terrain, or perhaps a kleptoparasite, using its size to steal kills from other predators like saber-toothed cats or dire wolves. The giant short-faced bear ranged across North America from Alaska to Mexico, wherever there were enough large herbivores to support such a massive predator. But like so many Ice Age megafauna, it went extinct around 11,000 years ago. Without the enormous herds of bison, horses, camels, and other prey that had sustained it, the short-faced bear couldn't survive. The last individuals died out as the Ice Age ended and ecosystems transformed, leaving behind only fossils and the knowledge that North America once hosted predators larger and more fearsome than anything alive on the continent today. There's a language written in the landscape, a grammar of shapes that tells you what forces created the terrain you're looking at. Rivers carve V-shaped valleys, steep sides meeting in a narrow bottom where the water flows, cutting downward over time through erosion. But glaciers create something entirely different. They carve U-shaped valleys, broad, flat bottoms with steep, almost vertical walls rising on either side. Once you know to look for this difference, you can read a landscape's history at a glance. Why the difference? Rivers erode primarily through the force of flowing water cutting into the streambed, carving downward along a narrow channel. But glaciers are different. A glacier fills an entire valley, ice pressed against rock on all sides, and as it flows, it grinds and plucks at the bedrock, not just at the bottom, but along the walls. The result is erosion that's more uniform, widening the valley while also deepening it, creating those characteristic U-shaped profiles. Many of the world's most dramatic valleys were carved by glaciers. Yosemite Valley in California, the Norwegian fjords, valleys throughout the Alps and the Rockies. When you stand at the bottom of one of these glacial valleys and look up at sheer walls rising thousands of feet on either side, you're seeing the work of ice that flowed through here during the Ice Age, grinding away rock, reshaping mountains, leaving behind a landscape that still reveals the power of glaciers thousands of years after they melted away. The valleys are signatures, evidence of ice that no longer exists, but that permanently altered the face of the earth. The Ice Age wasn't a single, stable period of cold. It was chaotic, unstable, marked by rapid swings between relatively warm and bitterly cold conditions. Ice cores from Greenland have revealed evidence of at least 25 abrupt warming events during the last glacial period, called Dansgaard-Oeschger events after the scientists who discovered them. These weren't gradual changes, they were shockingly rapid, with temperatures in Greenland jumping by as much as 15 degrees Celsius in just a few decades, possibly even faster. The pattern is striking. The climate would sit in a cold state for hundreds or thousands of years. Then abruptly it would warm, not to modern temperatures, but warm enough to make a dramatic difference. This warmer phase would last perhaps 200 to 1,000 years before gradually cooling again, eventually snapping back to full glacial cold, and then the cycle would repeat. The regularity is still not fully explained, but it appears to be linked to changes in ocean circulation, particularly in the North Atlantic, where shifts in currents could rapidly redistribute heat and trigger cascading climate effects. For Ice Age inhabitants, both humans and animals, this instability would have been challenging. Ecosystems would have constantly shifted. Animals adapted to cold would expand their ranges, then retreat. Forests would advance and withdraw. The landscape was never stable, never predictable on timescales of human lifetimes or even generations. It's a reminder that climate stability, the kind we've enjoyed for the past 11,000 years, is actually unusual. For most of the Ice Age, the climate was restless, swinging between states, never quite settling, creating a world of constant change. Deep in caves in France and Spain, hidden from daylight in chambers that require crawling through narrow passages to reach, are some of humanity's earliest artworks, painted tens of thousands of years ago by Ice Age people. These images show the animals they lived alongside: bison, horses, mammoths, rhinos, lions, bears, rendered with stunning accuracy and artistic sophistication. The artists understood perspective, shading, how to use the natural contours of cave walls to create three-dimensional effects. These aren't primitive scratchings, they're masterworks. What's remarkable is that both modern humans and Neanderthals created cave art. For a long time, art making was considered a uniquely modern human trait. something that separated us from other human species. But recent discoveries have complicated that picture. Some cave art in Spain has been dated to over 64,000 years ago, before modern humans had even arrived in Europe, meaning it must have been created by Neanderthals. Hand stencils, abstract designs, painted animals, Neanderthals were artists too. Why create art in deep caves, places that were difficult and sometimes dangerous to access? We don't know with certainty. Perhaps these were sacred spaces, places for rituals or ceremonies. Perhaps the act of creating the images was itself important, a way of connecting with the animal spirits, or ensuring successful hunts. Or perhaps it was something we can't easily understand from our modern perspective, motivations that made perfect sense to Ice Age people, but that are lost to us now. What's clear is that Ice Age humans, both modern humans and Neanderthals, had rich inner lives, symbolic thinking, aesthetic sensibilities. They were fully human in every way that matters, and they left behind art that still moves us thousands of years later. As glaciers flow over bedrock, they don't just scrape the surface. They grind rocks into progressively finer and finer particles through the immense pressure and friction of moving ice. The smallest of these particles, ground so fine they're almost like powder, is called rock flour or glacial flour. It's created at the base of glaciers, where ice meets bedrock, where rocks frozen into the bottom of the glacier act like sandpaper, pulverizing the bedrock beneath into particles sometimes finer than silt, almost as fine as clay. When this rock flour is carried away by meltwater and suspended in glacial streams and lakes, something beautiful happens. The particles are so fine and so light that they remain suspended in the water for long periods, scattering light in particular ways. The result is the distinctive turquoise or milky blue color of glacial lakes and rivers, that otherworldly, luminous quality that makes glacial water look like it's glowing from within. The water isn't dyed or tinted. It's literally filled with pulverized mountain, ground so fine it floats. You can see this effect in countless glacial lakes around the world. Lake Louise in Canada, Peyto Lake, the glacial rivers of Iceland, meltwater streams flowing from glaciers in Alaska and Patagonia. The color is so distinctive that it's a signature of active glaciation, a visual marker that glaciers are nearby, still grinding, still creating rock flour, and releasing it into the meltwater. And in a sense, you're looking at mountains being slowly destroyed, eroded grain by grain. The solid bedrock turned to floating powder that gives the water its ethereal, impossible blue. Antarctica, the frozen continent at the bottom of the world, buried under ice miles, thick, sterile, and lifeless, except at the edges where penguins gather. It seems like it's always been this way. A permanent, deep freeze, the coldest place on Earth. But Antarctica has a much stranger history. About 50 million years ago, Antarctica was green. Forests covered the continent, temperate beech forests similar to those in southern Chile or New Zealand today. The climate was mild, even warm. Rivers flowed. Animals lived there, including marsupials related to modern possums, and possibly even ancestors of modern Antarctic penguins when they could still fly. What changed? Continental drift. Antarctica, once connected to South America and Australia, gradually separated as the continents moved apart. Around 34 million years ago, the Drake Passage between Antarctica and South America opened wide enough to allow ocean currents to flow unimpeded around the continent. This created the Antarctic Circumpolar Current, a powerful current that circles Antarctica and effectively isolates it from warmer ocean waters to the north. Cut off from warm currents, Antarctica began to cool. Ice began to form, first in the mountains, then spreading across the continent. The forests died, the animals fled or went extinct, and within a few million years, Antarctica transformed from a green, forested continent to the frozen wasteland we know today. Buried under all that ice are the remains of that lost world. Fossilized tree trunks, leaf impressions, bones of animals that lived when Antarctica was warm. These fossils are difficult to access, requiring drilling through ice or finding rare exposed rock outcrops. But they're there, testament to a continent that once knew warmth and life, now locked in ice that may have been continuous for over 30 million years. Off the coast of Southern California are the Channel Islands, a chain of 8 islands separated from each other and from the mainland by miles of ocean. But during the Ice Age, when sea levels were 400 feet lower, these weren't 8 separate islands. They were one landmass called Santa Rosa, a single large island separated from the mainland by a narrow channel that was probably only about 6 miles wide at the narrowest point. And on this island lived mammoths. Not the enormous woolly mammoths of the mainland, but dwarf mammoths that stood only about 6 feet tall at the shoulder, roughly half the height of their ancestors. This is a phenomenon called island dwarfism, observed on islands around the world, when large animals become isolated on islands with limited resources and no large predators. Natural selection favors smaller body size. Smaller animals need less food, reproduce more quickly, and can sustain larger populations on limited resources. The Channel Island mammoths evolved from Columbian mammoths that somehow made it across the channel from the mainland, possibly swimming during a time when the channel was even narrower, possibly walking during an especially low sea level stand. Once isolated, they evolved over thousands of years into a distinct species, shrinking generation by generation. They survived on Santa Rosa until about 13,000 years ago, when they went extinct as the Ice Age ended, possibly from climate change, possibly from human hunting, possibly from some combination of factors. Today, all that remains are their bones, found in coastal cliffs and ancient sinkholes, evidence of an island ecosystem that existed for thousands of years and then vanished. Glacial ice isn't pure. It's not just frozen water. Embedded within it, frozen into the crystal lattice, or trapped in tiny air pockets, are all sorts of materials that fell from the sky or were picked up from the ground when the snow first fell. Mineral dust blown by wind, volcanic ash from eruptions thousands of miles away, pollen from plants, soot from ancient forest fires, sea salt carried inland by storms, and perhaps most remarkably, cosmic dust, microscopic particles from space that constantly rain down on Earth, the remnants of asteroids and comets that burn up in the atmosphere. Each layer of ice is like a snapshot of atmospheric composition at the moment that snow fell. By carefully analyzing the materials trapped in ice cores, scientists can reconstruct not just climate history, but also the history of volcanic eruptions, forest fires, desert dust storms, even variations in cosmic dust influx that might correlate with Earth passing through debris fields in space. It's an extraordinarily detailed record, preserved in frozen form, waiting to be read. Some of these particles are vanishingly small, requiring electron microscopes to study. Others are visible to the naked eye, small grains of sand or ash suspended in otherwise clear ice. And when very old ice melts, when glaciers that have existed for hundreds of thousands of years finally give up their ancient ice, these particles are released, dust from volcanic eruptions that happened before modern humans existed, cosmic visitors that arrived from space and were caught and held in ice for eons before finally being freed. The Great Lakes, Superior, Michigan, Huron, Erie, Ontario, contain about 21% of the world's surface fresh water, an enormous reservoir of water sitting in the heart of North America. These lakes seem permanent, ancient, as though they've always been there. But in geological terms, they're brand new, created by the ice sheets that advanced and retreated across North America during the Ice Age. They're scars left by glaciers, depressions, carved into bedrock and filled with meltwater when the ice finally retreated. The story is complex. The Great Lakes Basin had pre-existing river valleys, but glaciers deepened and widened these valleys, scouring out bedrock, creating the deep basins we see today. As ice sheets advanced, they pushed soil and rock ahead of them like bulldozers, creating moraines, ridges of debris that now form some of the southern boundaries of the lakes. And as the ice retreated, meltwater filled the depressions, creating a series of lakes that evolved over thousands of years as water levels changed and drainage patterns shifted. At various times, the lakes drained in different directions, sometimes into the Mississippi River system, sometimes into the St. Lawrence, sometimes creating temporary outlets that no longer exist. The current configuration of the Great Lakes, with drainage through the St. Lawrence River to the Atlantic, has only existed for about 8,000 years. Before that, the lakes were different sizes, at different levels, connected in different ways, and the land beneath them is still rising, still rebounding from the weight of ice that pressed it down, slowly changing the lakes even now. The Great Lakes are dynamic, still evolving, still responding to forces set in motion when the last ice age ended. South America during the Ice Age was home to some of the strangest megafauna on Earth, and among the strangest were the glyptodonts. Imagine an armadillo, then scale it up to the size of a small car. That's essentially what a glyptodont was, a massive, heavily armored mammal that could weigh over 2,000 pounds and measure 10 feet from nose to tail. But unlike armadillos, whose armor is made of flexible bands, glyptodont armor was fused into a solid dome, a thick carapace of interlocking bony plates that covered the entire body like a tank. And some species had weaponized tails. The tail wasn't just covered in armor. In some glyptodonts, it ended in a heavy club studded with bony knobs and spikes, similar to the tail clubs of ankylosaur dinosaurs. These clubs could have been used for defense against predators, or more likely, in combat with other glyptodonts, possibly battles over territory or mates. Fossil glyptodont shells sometimes show damage consistent with blows from tail clubs, evidence of violent encounters. Despite their fearsome appearance, glyptodonts were herbivores, grazing on grasses and low vegetation, lumbering slowly across South American grasslands and forests. They were successful for millions of years, but like so many Ice Age megafauna, they went extinct around 10,000 years ago, shortly after humans arrived in South America. Whether hunting pressure, climate change, or both caused their extinction remains debated. But for a time, South America was populated by these living tanks, bizarre echoes of the armored dinosaurs that had gone extinct 60 million years earlier. Convergent evolution creating similar solutions to the problem of defense. Not all cold periods are ice ages in the technical sense. The Little Ice Age, which lasted from roughly 1300 to 1850 CE, was a period of regional cooling, primarily affecting the northern hemisphere, that brought significantly colder winters and cooler summers compared to the medieval warm period that preceded it. It wasn't cold enough or long enough to create continent-spanning ice sheets, but it had dramatic effects on human societies and environments. Rivers that rarely or never froze began freezing regularly. The Thames River in London froze solid multiple times, thick enough that people held frost fairs on the ice, festivals with vendors, games, even an elephant walking on the frozen river in 1677. Glaciers in the Alps and elsewhere advanced, destroying villages and farmland that had been safely beyond the ice margin for centuries. Growing seasons shortened. Harvests failed more often. Some historians link the Little Ice Age to social upheaval, famines, and even events like the Salem witch trials, though these connections are debated. What caused it? Possibly decreased solar activity. The Little Ice Age coincided with the Maunder Minimum, a period when sunspots were unusually rare, suggesting the sun was putting out slightly less energy. Increased volcanic activity may have played a role, with ash in the atmosphere reflecting sunlight and cooling the planet. Or it might have been internal variability in Earth's climate system, natural fluctuations that happen without any specific external cause. By the mid-1800s, the Little Ice Age was ending, and the warming that has accelerated dramatically in recent decades began. But for 500 years, the world was noticeably colder, a reminder that climate is always changing, always restless. When ice sheets advance, they don't always follow the existing topography neatly. Sometimes they block rivers, creating natural dams of ice that trap meltwater and rainfall, forming lakes that can grow to enormous sizes. These are called proglacial lakes, lakes that exist at the margin of a glacier or ice sheet, held back by ice rather than rock or earth. And during the Ice Age, some of these lakes were absolutely massive, larger than any lakes that exist today. The largest was probably Lake Agassiz, which formed in central North America as the Laurentide ice sheet retreated. At its maximum extent, Lake Agassiz covered more area than all the current Great Lakes combined. Over 170,000 square miles of water, stretching across what is now Manitoba, Ontario, Saskatchewan, North Dakota, and Minnesota. It was deeper than Lake Superior in places, containing an almost inconceivable volume of water trapped behind ice dams and moraines. And it was unstable. As the climate warmed and the ice sheet continued retreating, the dams that held the lake back would occasionally fail, releasing catastrophic floods. These floods were among the largest in Earth's history, potentially dumping enough fresh water into the ocean to disrupt global ocean circulation and trigger rapid climate change events like the Younger Dryas. Eventually, as the ice sheet melted completely, Lake Agassiz drained away, its water flowing into Hudson Bay and the Atlantic. Today, only remnants remain. Lake Winnipeg, Lake Manitoba, Lake of the Woods, small fragments of what was once the largest lake in North America. In a world where glaciers are retreating almost everywhere, where ice loss is accelerating and climate change is warming the planet, there are a few anomalies, glaciers that are still advancing, growing thicker, pushing forward rather than retreating. The Hubbard Glacier in Alaska is one of these outliers, the largest tidewater glacier in North America, and it's been advancing for over a century, even as its neighbors shrink. Why? The answer is complex and has more to do with the glacier's specific geometry and snow accumulation patterns than with any local cooling. Hubbard Glacier has an enormous accumulation zone high in the mountains, where snow falls heavily and feeds the glacier. This feeding area is so productive that it supplies enough ice to keep the glacier advancing despite warming temperatures. The glacier flows down from the mountains and into the ocean, where it calves icebergs. But the rate of ice supply exceeds the rate of melting and calving, so the glacier continues to push forward. Occasionally, Hubbard Glacier advances far enough to block off Russell Fjord, temporarily damming it and creating a large lake. When this happens, the lake level rises, sometimes dramatically, until either the dam breaks and the lake drains in a catastrophic flood, or the glacier retreats slightly and opens the fjord again. This has happened several times in recent decades, most notably in 1986 and 2002, creating temporary lakes that lasted weeks or months before draining. It's a reminder that even in a warming world, glaciers are complex systems, and local factors can sometimes override global trends, at least temporarily. When ice sheets lock up enormous amounts of water, the entire global water cycle slows down. Less water evaporates from cold oceans. Less moisture is carried by atmospheric circulation to the continents. Rainfall decreases in many regions, particularly in the tropics and subtropics. The result is that during glacial maxima, when ice coverage was at its peak, the world wasn't just colder, it was also much drier overall. Deserts expanded. The Sahara grew larger. The deserts of Australia, Central Asia, the American Southwest, all expanded beyond their current boundaries. Areas that today receive enough rainfall to support grassland or scrub woodland became desert or near desert. Sand dunes advanced, lakes dried up. Rivers that flow year-round today became seasonal or disappeared entirely. Evidence of this drier Ice Age world is preserved in sediment cores, fossil sand dunes now buried or stabilized, and dry lake beds that show ancient shorelines far below any historical water levels. This creates an interesting paradox. We tend to think of the Ice Age as a time of abundant water. After all, so much water was locked up in ice, but most of that water was removed from circulation, taken out of the ocean and the atmosphere and frozen into ice sheets. The parts of the world that weren't under ice were often drier, harsher, more challenging for life than they are today. The modern world, with its current distribution of rainfall and its currently sized deserts, is actually wetter and more hospitable than the Ice Age world was for most regions. We live in a relatively generous climate, at least from the perspective of water availability. Among the strange and wonderful creatures of the Ice Age, the woolly rhinoceros holds a special place. A massive, shaggy beast perfectly adapted to life in the frozen north. Like woolly mammoths, woolly rhinos were covered in thick fur, 2 layers of it, a dense undercoat for insulation, and longer guard hairs to shed rain and snow. They had small ears to minimize heat loss, a stocky build for conserving warmth, and a thick layer of fat beneath the skin for both insulation and energy storage during harsh winters. But the most striking feature was the horn, Woolly rhinos had two horns, actually, but the front horn was enormous, flattened from side to side rather than circular in cross-section, and could grow to over 3 feet long. What did they use such a massive horn for? We're not entirely certain. Modern rhinos use their horns for defense, for fighting over mates, and for clearing vegetation. Woolly rhinos might have used their horns similarly, but there's also evidence they used them to sweep snow aside to reach vegetation beneath. Cave paintings and frozen specimens show wear patterns on the horn tips consistent with this behavior. These animals ranged across the mammoth steppe from northern Europe to Siberia, grazing on the tough grasses and shrubs of Ice Age, tundra, and steppe. We know what they looked like with remarkable detail because, like mammoths, some woolly rhinos have been found frozen in Siberian permafrost, their bodies preserved with skin, fur, and even stomach contents intact. They survived until about 10,000 years ago before going extinct, likely due to climate change and habitat loss as the Ice Age ended, and their preferred cold grasslands transformed into forests and wetlands. The Ice Ages we've been discussing, the recent cycles of the Pleistocene, the ice sheets of the last glacial maximum, these are actually quite mild compared to some ice ages in Earth's deep past. About 700 million years ago, during a time called the Cryogenian period, Earth may have experienced the most extreme ice ages in its history. Events so severe that ice may have extended from the poles all the way to the equator, encasing the entire planet in a frozen shell. These are called snowball Earth events. Evidence for snowball Earth comes from glacial deposits, rocks that were clearly deposited by glaciers, found in locations that were at the equator when those rocks formed. Glaciers at the equator suggest a level of cold almost unimaginable, a planet so frozen that even the tropics were iced over. Computer models suggest that once ice extends beyond about 30 degrees latitude, a runaway feedback loop occurs. Ice reflects so much sunlight that the planet cools further. Ice advances more, and the process accelerates until the entire surface is frozen. How did Earth escape from such extreme glaciation? Probably through volcanic activity. Even with the surface frozen, volcanoes would continue erupting, releasing carbon dioxide into the atmosphere. Normally, weathering of rocks removes CO2, but with the surface frozen, weathering would have stopped. CO2 would have accumulated over millions of years until the greenhouse effect became strong enough to start melting the ice. And once melting began, the reverse feedback would occur. Less ice means less reflection, more warming, more melting, until the planet thawed completely. Snowball Earth events were planetary-scale catastrophes, but life survived them, possibly in refuges near volcanic vents or in the ocean beneath the ice. And when the ice finally melted, life exploded in diversity, perhaps spurred by the extreme selective pressure of surviving such conditions. Beneath your feet in Greenland, if you were standing on the ice sheet, are layers upon layers of compressed snow, year after year, decade after decade, century after century, going back in time as you go deeper. At the surface, fresh snow from this year. A few feet down, snow from a decade ago. Hundreds of feet down, snow from thousands of years ago. And at the very bottom, pressed against the bedrock over 2 miles below the surface, ice that fell as snow during the last interglacial period, over 100,000 years ago. This ice is an archive of extraordinary value. Each layer represents 1 year's snowfall, and trapped within that snow are air bubbles containing atmospheric gases, dust particles carried by wind, volcanic ash, sea salt, pollen, everything that was in the air when that snow fell. By drilling cores through the entire thickness of the ice sheet, scientists can extract this record and read it like a history book, learning about temperature, precipitation, atmospheric composition, volcanic eruptions, even forest fire activity, going back 100,000 years or more. The deepest, oldest ice is fragile, thinned and deformed by the weight of all the ice above it, sometimes folded or disrupted, making interpretation challenging. And as the climate warms, this ice is at risk. If the Greenland ice sheet melts, not all at once, but over centuries or millennia of continued warming, this archive will be lost forever. The only record of that Ice Age interglacial period, the only direct samples of a 100,000-year-old atmosphere, will melt and flow into the ocean, irretrievably gone. Scientists are racing to extract and preserve as much information as possible while the ice still exists. Extinction isn't always a single event. Sometimes it's a process, a slow dwindling as circumstances turn against a species. For saber-toothed cats, the end came around 10,000 years ago as the Ice Age was ending and the world was transforming rapidly. These cats had been apex predators for millions of years, successful across multiple continents, perfectly adapted to hunting the large, thick-skinned herbivores that dominated Ice Age ecosystems. But then those herbivores began disappearing. As the climate warmed and forests expanded, the large herbivores that saber-toothed cats specialized in hunting, mammoths, mastodons, giant ground sloths, ancient bison and horses, declined in numbers or went extinct entirely. This might have been due to climate change, to human hunting, to disease, or to some combination of all three. But whatever the cause, the prey base that had sustained saber-toothed cats for so long was vanishing. And these cats were specialists, with those long, fragile teeth adapted for very specific killing techniques on very specific types of prey. When their prey disappeared, saber-toothed cats couldn't easily adapt. They couldn't switch to hunting smaller, faster prey the way more generalized predators could. Their teeth were too specialized, their hunting strategy too specific. Populations declined. The last saber-toothed cats starved or failed to reproduce successfully. And around 10,000 years ago, the last individual died, ending millions of years of evolutionary history. Today, we know them only from fossils, from bones in tar pits and caves, from the rare frozen specimens in permafrost. They were magnificent predators, but in the end, being too specialized for a particular world meant they couldn't survive when that world changed. When we think of Ice Age landscapes, we often picture tundra, low-growing vegetation, mosses and lichens, shrubs but few trees, the kind of ecosystem we see today in Arctic regions north of the tree line. But surprisingly, tundra as we know it didn't really exist during much of the Ice Age. The regions beyond the ice sheets were often too dry and too cold even for tundra. Instead, a unique ecosystem called the Mammoth Steppe dominated vast areas of the northern hemisphere. The Mammoth Steppe was unlike anything we have today, a cold, dry grassland with scattered shrubs, supporting enormous biomass of large herbivores. It wasn't quite tundra, wasn't quite steppe, but something in between, a vanished ecosystem with no modern equivalent. The vegetation was probably dominated by grasses, herbs, and sagebrush, kept relatively open by grazing pressure from mammoths, horses, bison, and other megafauna. The animal density may have rivaled the African Serengeti, except in a much colder climate. When the Ice Age ended and the megafauna went extinct, this ecosystem collapsed. Without the constant grazing pressure, without the animals to maintain the grasslands, the vegetation changed. In some areas, forests advanced. In the coldest regions, tundra replaced the mammoth steppe, a wetter, mossier ecosystem with much lower productivity. The tundra we see today in the Arctic is not a relic of the Ice Age, but actually a post-Ice Age development, formed only after the mammoth steppe ecosystem died out with the animals that had maintained it. Scattered across landscapes in the northern hemisphere are boulders that don't belong. They're made of rock types that don't match the local geology, sometimes composed of stone found nowhere nearby, sitting incongruously on different bedrock or in the middle of farmland or forest. These are glacial erratics, and they're one of the most visible signs that glaciers once covered these regions. Glaciers are powerful enough to pluck boulders, some of them enormous, weighing hundreds or even thousands of tons, from bedrock, freeze them into the ice, and carry them for miles or even hundreds of miles as the glacier flows. When the glacier finally melts, it deposits these boulders wherever the ice happens to release them, leaving them stranded far from their point of origin. Before the Ice Age theory was accepted, these boulders were deeply puzzling. How did massive rocks end up in places where that type of rock doesn't exist? Some attributed them to Noah's flood. Others proposed catastrophic events beyond imagining. But once scientists understood glacial transport, erratics became useful. By identifying the source of an erratic boulder and mapping where it was deposited, you can trace the path of ancient glaciers, determine which direction the ice flowed, and reconstruct ice sheet extent. Some erratics have become famous landmarks. Plymouth Rock in Massachusetts is probably a glacial erratic, though its exact origin is uncertain. Others are tourist attractions, massive boulders balanced improbably on pedestals of different rock. They're messages from the Ice Age, geological postcards telling us that ice was once here, powerful enough to move mountains, or at least to move pieces of them. If you wanted to define the Ice Age in geological terms, you'd be talking about the Pleistocene epoch, a span of time from about 2.6 million years ago to 11,700 years ago, when Earth's climate was dominated by repeated glacial-interglacial cycles. The Pleistocene is the epoch of ice ages, the time when glaciers advanced and retreated across the northern continents in rhythmic patterns driven by orbital cycles and feedback loops in Earth's climate system. And it's the epoch during which our genus, Homo, evolved and diversified. Early humans appeared in Africa just as the Pleistocene was beginning, and the entire history of our evolutionary lineage unfolded against the backdrop of Ice Age climate swings. We evolved during unstable climates, learning to adapt to dramatic environmental changes, developing larger brains and more sophisticated tools and social structures, partly in response to the challenges of living in a world where the climate could shift dramatically within a few human lifetimes. The Pleistocene ended 11,700 years ago when the last glacial period gave way to the current, warm interglacial, which we call the Holocene epoch. That's the world we've lived in ever since, a warm, relatively stable climate that allowed agriculture to develop, civilizations to rise, and human population to explode from a few million to over 8 billion. But the Pleistocene shaped us. We are, in a fundamental sense, Ice Age creatures, products of a time when survival meant adapting to a restless, changing world. And perhaps that adaptability, forged in Ice Age climates, is why we've been so successful in the warm stability that followed. Mastodons and mammoths are often confused with each other, both being large, elephant-like creatures with tusks and trunks that lived during the Ice Age. But they were actually quite different animals, only distantly related, and they occupied different ecological niches. One of the most revealing differences is in their teeth. Look at a mastodon tooth and you'll see cone-shaped cusps arranged in rows, designed for crushing and grinding leaves, twigs, and woody vegetation. These are browsing teeth, the teeth of an animal that fed on shrubs and trees. Mammoth teeth are completely different. They're made up of thin, parallel plates of enamel, sometimes as many as 30 plates in a single tooth, creating a surface perfect for grinding tough, abrasive grasses. These are grazing teeth, evolved for an animal that spent most of its time eating grass. This difference in diet meant that mastodons and mammoths could coexist in the same regions without directly competing. Mastodons preferred forests and woodlands, feeding on shrubs and low-hanging branches. Mammoths lived on open grasslands and steppes, grazing like modern bison or cattle. And there's something poignant in this difference, because it helps explain why both went extinct. As the Ice Age ended and forests expanded in some regions while grasslands persisted in others, the habitats that had supported these animals fragmented and changed. Mastodons lost their forests. Mammoths lost their grasslands. Both species, perfectly adapted to Ice Age ecosystems, found themselves in a rapidly changing world where their preferred foods were disappearing. Those specialized teeth, so perfectly suited to their diets, became liabilities when the plants they were designed to process vanished from the landscape. Long before paleontology existed as a science, people found mammoth remains, enormous bones and tusks emerging from riverbanks, thawing out of permafrost, uncovered by erosion. And they created stories to explain these finds. In Siberia, where mammoth remains are particularly common, the word mammoth derives from mamut or mamont, which may come from an old word meaning earthhorn. The idea was that these creatures lived underground, burrowing through the earth like enormous moles, and died when they accidentally surfaced and were exposed to light or air. It's a fantastical explanation, but in the absence of any concept of extinction or deep geological time, it made a kind of sense. The tusks and bones were found in the ground, buried in earth or frozen in permafrost. The creatures were clearly enormous, far larger than any living animal known to Siberian peoples. Why not imagine them as subterranean dwellers whose remains appeared when their tunnels collapsed or when they accidentally burrowed too close to the surface? Similar myths existed in other cultures. Some thought mammoth bones were the remains of giant humans or of mythological creatures. It wasn't until the 18th and 19th centuries that scientists began to understand what mammoths really were: extinct relatives of modern elephants, adapted to cold climates, that had once lived on the surface in vast numbers. The recognition that animals could go extinct, that entire species could vanish from the earth, was itself a revolutionary concept. And mammoths became some of the most important evidence for extinction and for the idea that Earth had a deep history of life forms that no longer existed. The myths about earth horns and burrowing giants gave way to a stranger, more wonderful truth, that the world was once populated by creatures that no living person had ever seen. Ice Age Earth was a dusty place, with so much land exposed by low sea levels, with vast areas of bare ground beyond the ice sheets, ground that was too cold and dry for extensive vegetation. Strong winds picked up enormous quantities of dust and carried it across continents. This fine-grained sediment, mostly silt-sized particles, was transported by wind and deposited in thick blankets called loess, which accumulated in some regions to depths of hundreds of feet. The loess deposits in China are among the most extensive in the world, covering about 10% of the country's land area and reaching depths of over 300 feet in some locations. Each layer of loess represents a glacial period when dust was actively being deposited. Between the lowest layers are thinner layers of soil that formed during warmer, wetter interglacial periods when vegetation stabilized the surface and dust deposition slowed. This alternating pattern creates a detailed climate record stretching back hundreds of thousands of years, readable in the layers of dust and soil. Walking through loess deposits can feel surreal. Entire landscapes, whole plateaus and hills, built not from bedrock but from dust, from countless particles of ground-up rock carried by ice age winds and slowly accumulated over tens of thousands of years. Rivers have carved deep canyons through loess, revealing the layers in cross-section, showing the history of dust deposition like pages in a book. And loess makes excellent agricultural soil. It's fertile, well-drained, easily worked. Much of the agricultural productivity of northern China, the American Midwest, and other regions owes itself to Ice Age dust, to wind-borne sediment deposited during the coldest, driest periods of glaciation. Among Ice Age predators, the cave lion stands out as one of the most formidable. Despite the name, cave lions didn't actually live in caves. They're called that because their remains are often found in caves, either because they sheltered there occasionally, or because their bones were carried there by scavengers or floods. Cave lions were enormous, among the largest cats that have ever lived, standing about 4 feet tall at the shoulder and measuring over 7 feet long, not including the tail. They were 25% or more larger than modern lions, powerful predators that hunted across the mammoth steppes of Ice Age Europe and Asia. What's fascinating is the evidence about their appearance. Cave paintings created by Ice Age humans show lions that appear to lack manes, or at most have very small manes. Additionally, a nearly perfectly preserved cave lion cub, found frozen in Siberian permafrost, showed no evidence of developing a mane. This suggests that, unlike modern male lions, which have prominent manes, cave lion males may have been maneless or nearly so. Why? Perhaps the cold climate made a thick mane less necessary for warmth when the entire body was already adapted to cold. Or perhaps the social structure was different, and manes weren't needed as signals in the same way they are for modern lions. These animals hunted the megafauna of the Ice Age: young mammoths, horses, bison, reindeer. They were apex predators with few threats except perhaps from other predators or from the dangerous prey they hunted, and they survived until remarkably recently. The last cave lions went extinct only about 14,000 years ago, persisting thousands of years longer than many other megafauna. For a time, humans and cave lions shared the European landscape, competing for prey, occasionally coming into conflict, and perhaps occasionally hunting each other. From the ground, a glacier or ice sheet might appear static, motionless except for the occasional crack or calving event. But from above, from satellites or aircraft, glaciers reveal themselves as dynamic, flowing rivers of ice with distinct patterns and structures. Ice doesn't just pile up randomly. It flows outward from areas of maximum accumulation, typically high in mountains or in the cold centers of ice sheets, following the pull of gravity and spreading under its own weight. This flow creates visible patterns. Crevasses form where ice flows over uneven bedrock, or where flow rates change. Medial moraines, stripes of dark sediment, form where two glaciers merge, marking the boundary between ice from different sources. Ogives, curved patterns on some glaciers, form as ice passes through ice falls and gets compressed and stretched in regular cycles. From space, these patterns are beautiful, abstract art created by the physics of ice movement, revealing the hidden currents and streams within what appears solid. And the ice preserves a memory of its journey. Ice that fell as snow at the top of a glacier thousands of years ago slowly flows downward and outward, spending centuries or millennia traveling from the accumulation zone to the ablation zone where it finally melts. Within that ice is trapped air from the atmosphere that existed when it first fell, dust from ancient storms, information about climate and environment frozen in place. When that ice finally melts at the glacier's terminus, it releases water and sediment that originated high in the mountains decades or centuries earlier. Glaciers are time machines, moving through space and preserving time. The end of the Ice Age wasn't just a climate transition, it was an extinction event. Between about 50,000 and 10,000 years ago, depending on the region, the majority of large mammal species on Earth went extinct. The timing varied by continent. Australia lost its megafauna earliest, around 45,000 years ago. Eurasia lost species gradually over tens of thousands of years. The Americas saw the most concentrated extinctions around 11,000 years ago. But the pattern was consistent. The large animals disappeared, and in some regions, the losses were catastrophic. North America lost about 70% of its large mammal genera. Mammoths, mastodons, saber-toothed cats, giant ground sloths, horses, camels, giant short-faced bears, dire wolves, American lions, and many more. South America's losses were even more severe, approaching 90%. Australia lost virtually all of its megafauna: giant wombats, marsupial lions, enormous kangaroos. Only Africa retained most of its large mammals, though even there, some species went extinct. What caused this? The debate has raged for decades. Was it climate change? The transformation of ecosystems as the Ice Age ended? Was it human hunting? People spreading across the world and killing megafauna faster than they could reproduce? Was it disease? Some combination of all three. The timing is suspicious. Extinctions often follow shortly after humans arrive in a region. But climate change at the end of the Ice Age was also dramatic and rapid. Most likely, it was a combination, with different factors dominating in different regions. But whatever the cause, the result was clear. The Ice Age megafauna, animals that had survived for millions of years through multiple glacial cycles, couldn't survive this final transition. The world that emerged from the Ice Age was profoundly different, emptier, missing the giants that had defined Ice Age ecosystems. Trees need moisture and warmth, at least during the growing season. During glacial periods, when the climate was colder and drier, forests couldn't maintain themselves across their current range. In many regions, forests contracted to refugia, isolated pockets of favorable habitat, often in river valleys or on sheltered slopes, while grasslands expanded dramatically. The Ice Age world was dominated by open landscapes, steppes, grasslands, tundra, savannas. This transformation had profound effects on evolution and ecology. Grasslands support different communities of animals than forests do. Grazers, animals that eat grass, thrived and diversified. Horses, bison, mammoths all reached enormous population sizes on Ice Age grasslands. Predators adapted to hunting in open terrain, relying on speed and pack hunting rather than ambush. Even birds evolved to take advantage of these open landscapes, with some species specializing in grassland habitats that barely exist today, and humans adapted too. Many researchers think that the expansion of grasslands influenced human evolution, favoring bipedalism and long-distance running, traits that are advantageous in open terrain. Our ancestors evolved in Africa during a time when grasslands and savannas were expanding, and many of the traits that make humans distinctive, our upright posture, our endurance running abilities, our tool use, may be partly adaptations to life in open, grassy environments. When the Ice Age ended and forests expanded again, the world changed dramatically. Animals adapted to open grasslands had to retreat or adapt. Some couldn't, and they went extinct. The modern world, with its extensive forests, is actually unusual compared to most of the past 2 million years. The Earth's crust isn't completely solid and rigid. On geological timescales, it behaves more like a very thick, viscous fluid, capable of flowing slowly in response to pressure. During the Ice Age, the Scandinavian ice sheet was over 2 miles thick in places, pressing down on the crust with enormous weight. That weight pushed the crust downward into the semi-molten mantle below, depressing the land surface by hundreds of feet. When the ice melted, the pressure was released, and the crust began slowly rising back to its original position, a process called isostatic rebound or post-glacial rebound, and it's still happening. Scandinavia is still rising, about 1 centimeter per year in some locations, thousands of years after the ice melted. GPS measurements confirm it. The land is moving upward, measurably, continuously. Harbors built by the Vikings are now high and dry, well above sea level. Islands are growing larger as their coastlines rise. Relative sea level is falling in some areas even as global sea level rises, because the land is rising faster than the ocean. This process will continue for thousands of years more, gradually slowing as the crust approaches equilibrium. But it's already had 10,000 years to rebound, and it's still not finished, testament to the enormous weight the ice exerted and to the viscosity of the mantle, which flows so slowly that full equilibration takes tens of thousands of years. The same process is happening in other formerly glaciated regions: Canada, northern Scotland, parts of Russia. The Earth remembers the ice, and it's still adjusting, still recovering, still responding to forces that ceased thousands of years ago. Not everywhere was frozen during glacial maxima. Even at the peak of ice ages, there were pockets of more favorable habitat, regions where local climate or geography created conditions warm or sheltered enough for animals and plants to survive, even when conditions in surrounding areas were too harsh. These refugia served as sanctuaries, preserving species through the worst of glacial conditions. Refugia could be small, a single sheltered valley, a south-facing slope that received more sunlight, an area warmed by ocean currents or geothermal activity. Or they could be larger regions where climate remained relatively moderate. Southern Europe, for instance, served as a refugium for many tree species during glacial periods. When ice covered northern Europe, forests retreated to Italy, Spain, the Balkans, and other southern areas. When the climate warmed, trees spread northward from these refugia, recolonizing formerly glaciated regions. The genetic signatures of refugia are still visible today. Species that survived in isolated refugia often show distinct genetic lineages corresponding to different refugia. Populations that were separated for thousands of years and evolved slight differences before coming back into contact when conditions improved. By studying these genetic patterns, scientists can identify where refugia existed and trace how species recolonized their ranges after the ice retreated. In essence, DNA carries a memory of the Ice Age, a record of where populations sheltered and how they spread when the world warmed again. Today, Australia, Tasmania, and New Guinea are separate land masses separated by seas. The Bass Strait between Australia and Tasmania, the Torres Strait between Australia and New Guinea. But during the last glacial maximum, when sea levels were 400 feet lower, these barriers didn't exist. The three land masses were connected, forming a single continent called Sahul. You could have walked from modern-day Melbourne to Tasmania to Papua New Guinea without ever seeing the ocean, traveling across land that is now beneath the sea. Sahul was enormous, about 40% larger than modern Australia. It included vast areas of now submerged land on the continental shelf, particularly in the north between Australia and New Guinea. These weren't just narrow land bridges. They were extensive lowlands with rivers, lakes, and ecosystems. Aboriginal Australians lived on Sahul, their territories extending across areas that are now underwater, their sacred sites and hunting grounds drowned when sea levels rose. When did Sahul exist? Throughout most of the Ice Age, whenever sea levels were low enough, which was most of the time during glacial periods. It only fragmented into separate islands relatively recently, as the Ice Age ended and glaciers melted and sea levels rose. The flooding happened gradually over thousands of years, but fast enough that people would have noticed the ocean encroaching, claiming land, cutting off populations. Stories preserved in Aboriginal oral traditions may reference this flooding, describing times when the ocean rose and separated lands that were once connected. Stories that might preserve memories of events that happened 8,000 to 10,000 years ago, passed down through hundreds of generations. When we imagine ice, we usually picture something uniform, solid all the way through, frozen completely. But glacial ice is far more complex. As snow accumulates and transforms into ice over centuries, it creates layers of varying density and composition. Some layers are more compressed than others. Some contain more air bubbles. Some have different crystal structures depending on the conditions when they formed. And surprisingly, deep within some glaciers and ice sheets, there are pockets of liquid water that have been isolated from the outside world for hundreds of thousands of years. These water pockets form when pressure and geothermal heat from Earth's interior melt ice at the base of thick glaciers. The ice above acts as a seal, preventing the water from refreezing or escaping. In Antarctica, there are entire subglacial lakes, Lake Vostok being the most famous, containing liquid water that has been isolated for potentially millions of years. This water exists in complete darkness, under enormous pressure, cut off from the atmosphere and surface environment, since before modern humans existed. Scientists are intensely interested in these ancient water pockets because they might harbor unique microbial life, organisms that have evolved in isolation in one of Earth's most extreme environments. Sampling this water is extraordinarily difficult. You have to drill through miles of ice without contaminating the pristine water below. But the potential discoveries make it worthwhile. If life exists in these ancient, sealed environments, it might give us clues about how life could survive in similar environments on other worlds under the ice of Europa or Enceladus, moons of Jupiter and Saturn, where subsurface oceans might exist beneath frozen shells. Some Ice Age animals survived far longer than mammoths or saber-toothed cats, persisting not just through the end of the Ice Age, but well into recorded human history. The auroch, Bos primigenius, was one of these survivors. These massive wild cattle stood over 6 feet tall at the shoulder, with long, forward-pointing horns that could span over 3 feet. They were powerful, aggressive animals, described in historical accounts as fierce and dangerous, not at all like the docile domestic cattle descended from them. Aurochs ranged across Europe, Asia, and North Africa, surviving the transition from Ice Age to the modern world. They're depicted in Ice Age cave paintings alongside mammoths and horses, showing that early humans knew them well. And eventually, around 8,000 years ago in the Near East, humans managed to domesticate aurochs, selectively breeding them over generations into the various breeds of cattle we know today. But the wild aurochs persisted alongside their domestic descendants for thousands of years. Gradually, though, their range shrank. Hunting pressure increased. Forests were cleared for agriculture, reducing their habitat. By medieval times, aurochs survived only in isolated populations in Eastern Europe. The last wild auroch population lived in the Jaktorów forest in Poland, protected by royal decree. But even protection couldn't save them. Disease, inbreeding in the small remaining population, and continued habitat loss took their toll. On May 21, 1627, the last known auroch, a female, died in Poland. An animal that had survived the entire Ice Age, that had witnessed the rise and fall of countless human civilizations, was gone. We know exactly when the last one died, but we couldn't save it. The ocean isn't static. It's constantly moving, driven by wind, by temperature differences, by salinity variations. Warm water flows from the tropics toward the poles. Cold, dense water sinks and flows along the ocean floor back toward the equator. These circulation patterns, collectively called thermohaline circulation, distribute heat around the planet and profoundly influence climate. During ice ages, these patterns were dramatically different from today, with consequences that rippled through the entire climate system. The Atlantic meridional overturning circulation, which includes the Gulf Stream, brings warm tropical water northward and releases heat to the atmosphere, warming Europe and North America. During glacial periods, this circulation weakened or shifted. Massive amounts of fresh water from melting ice sheets poured into the North Atlantic, making the surface water less dense and interfering with the sinking of cold water that drives the circulation. When the circulation weakened, less heat was transported northward, and the northern hemisphere cooled further, a feedback loop that amplified glaciation. Evidence from sediment cores shows that ocean circulation has repeatedly shut down or dramatically reorganized during ice ages, sometimes quite abruptly. These circulation changes are linked to some of the rapid climate shifts recorded in ice cores, the Dansgaard-Oeschger events, and the Younger Dryas cooling. The ocean is a major player in climate, storing enormous amounts of heat and carbon dioxide, and when its circulation patterns change, the entire planet feels the effects. Understanding how ocean circulation responded to Ice Age conditions helps scientists predict how it might respond to current climate change, particularly to the increasing freshwater input from melting ice sheets. The underside of a glacier isn't smooth ice. It's often embedded with rocks, everything from fine sediment to massive boulders, frozen into the ice at the base where the glacier meets bedrock. As the glacier flows, these embedded rocks act like the teeth on a file or the grit on sandpaper, grinding against the bedrock beneath. This process, called abrasion, is one of the main ways glaciers erode rock and reshape landscapes. The embedded rocks carve scratches into the bedrock called glacial striations, long parallel grooves that can be inches deep and hundreds of feet long. When you see striations on exposed bedrock, you can determine which direction the glacier was flowing based on the orientation of the scratches. The same abrasion process also polishes rock surfaces smooth, creating the characteristic smooth, rounded bedrock surfaces you see in formerly glaciated regions. Sometimes the polishing is so effective that the bedrock gleams almost like marble, reflecting light, still smooth thousands of years after the ice melted. At the same time, the glacier is also plucking larger chunks of rock from the bedrock, a process called quarrying or plucking. Water seeps into cracks in the bedrock, freezes to the base of the glacier, and then the moving ice pulls the rock fragments away. The combination of plucking and abrasion allows glaciers to erode bedrock at impressive rates, carving deep valleys, creating the distinctive landscapes we associate with glaciation. And the sediment produced by all this grinding, the rock flour and larger fragments, gets transported by the glacier, sometimes for hundreds of miles, before being deposited as glacial till when the ice finally melts. When we think of beavers, we picture relatively small, industrious rodents, maybe 50 or 60 pounds, building dams and lodges. But the giant beaver of Ice Age North America, Castoroides ohioensis, was something else entirely. These animals could reach 7 feet in length and weigh 200 pounds or more, making them the size of modern black bears. They were the largest rodents in North America during the Ice Age, and among the largest rodents that have ever lived anywhere. Despite their size, giant beavers were still aquatic animals. They had webbed feet, lived near water, and were excellent swimmers. Their teeth were enormous, incisors up to 6 inches long, though interestingly, the wear patterns on these teeth suggest they weren't using them to cut down trees the way modern beavers do. The teeth show more vertical wear, consistent with cutting softer aquatic vegetation. Giant beavers probably fed on water plants, roots, and wetland vegetation rather than tree bark and wood. Did they build dams and lodges like modern beavers? We're not certain. No preserved giant beaver dams have been found, but that doesn't mean they didn't build them. Organic structures like dams decompose and rarely fossilize. What we do know is that they lived in wetland environments across much of North America, from Alaska to Florida, wherever there were suitable aquatic habitats. And like so many other megafauna, they went extinct around 11,000 years ago, disappearing as the Ice Age ended and wetland environments changed. The last giant beavers vanished, and modern beavers, so much smaller but in many ways more behaviorally sophisticated, survived to become the dam-building landscape engineers we know today. Plants produce pollen, often in enormous quantities, that gets dispersed by wind or animals. Most of it falls to the ground or into water, where it settles into sediment and becomes buried. And pollen is remarkably resistant to decay. The outer wall of pollen grains is made of a substance called sporopollenin, one of the most chemically resistant biological materials known. Pollen grains can survive buried in sediment for millions of years, preserving not just their shape, but their distinctive features that allow identification to genus or even species level. By extracting cores of sediment from lake bottoms or peat bogs and analyzing the pollen in each layer, scientists can reconstruct past vegetation with remarkable detail. Each layer represents a different time period, and the pollen in that layer tells you what plants were growing in the region when the sediment was deposited. If you find pine pollen, there were pine forests nearby. If you find grass pollen, the landscape was more open. If you find tundra plants, the climate was cold. This has allowed scientists to trace how plant communities shifted during Ice Age climate cycles. They can see forests retreating to refugia during cold periods and expanding again during warm periods. They can track the migration of tree species as climates changed, watching as oaks or beeches spread northward after the ice retreated, advancing at rates of hundreds of yards per year over thousands of years. They can identify when agriculture began in a region by looking for sudden increases in grass and weed pollen that accompany farming. Pollen is a botanical time machine, each microscopic grain a messenger from the past, telling us what the landscape looked like when it fell from a flower that bloomed thousands of years ago. If you could choose a single moment to represent the peak of the Ice Age, it would be around 21,000 years ago, the last glacial maximum, or LGM. This was when ice sheets reached their greatest extent, when the most water was locked up in ice, when sea levels were lowest, when global average temperatures were coldest. It was the culmination of tens of thousands of years of cooling and ice sheet growth. But here's something counterintuitive. Global average temperatures during the LGM were only about 8 to 10 degrees Fahrenheit colder than today. Just 8 to 10 degrees. That doesn't sound like much. It's the difference between a cool day and a cold day, a variation you might experience between morning and afternoon. Yet this seemingly small difference was enough to completely transform the planet, to bury continents under ice, to lower sea levels by 400 feet, to create ecosystems unlike anything that exists today. Why such dramatic effects from such a modest temperature change? It's about feedbacks and thresholds. Small changes in temperature affect where snow can persist through summer. Areas that barely melted snow previously now retain it. Snow reflects sunlight, cooling the region further, allowing more snow to accumulate. Ice sheets grow. They create their own cold climate, chilling the surrounding air. The process accelerates. Within the climate system, there are tipping points where small changes cascade into large effects. And apparently, a shift of 8 to 10 degrees in global average temperature is enough to push the climate from interglacial warmth to full glacial conditions. It's a sobering reminder that Earth's climate is more sensitive than it might appear, that changes that seem modest numerically can have overwhelming consequences. Lakes fed by glacial meltwater are harsh environments. The water is extremely cold, often close to freezing year-round. It's often turbid with rock flour, limiting light penetration. Nutrient levels can be low, yet life finds a way, and some glacial lakes have developed unique ecosystems with species found nowhere else, adapted to these extreme conditions over thousands of years of isolation. Lake Vostok in Antarctica, buried under more than 2 miles of ice, has been isolated from the surface for possibly 15 million years. We don't know yet what lives there, but if there's life, it would represent one of the longest isolated ecosystems on Earth. In more accessible glacial lakes, scientists have found unique communities of microorganisms, some of them using chemical reactions rather than photosynthesis for energy in the dark, cold environments. Some fish species in glacial lakes show adaptations to cold that aren't seen in their relatives in warmer waters. Antifreeze proteins in their blood, slower metabolisms, different reproductive strategies. These glacial lake ecosystems are windows into how life adapts to extreme conditions, and they're also threatened. As glaciers melt and retreat with climate warming, glacial lakes are changing. Some are warming, losing their glacial characteristics. Some are draining as ice dams fail. The unique species adapted to glacial conditions may have nowhere to go, no other suitable habitat. They're relics of the Ice Age, hanging on in isolated pockets, and as the world warms, they may disappear before we fully understand them, taking with them unique evolutionary solutions to the problem of surviving in one of Earth's most challenging environments. Try to imagine the dominant ecosystem of Ice Age Northern Hemisphere, and you might picture tundra like we see in the Arctic today. Low-growing plants, mosses, lichens, wet and cold. But that's not quite right. The dominant ecosystem was something called the Mammoth Steppe, and it was unlike anything that exists today. It was a cold, dry grassland with scattered shrubs and occasional trees, supporting a productivity and biodiversity of large mammals that has no modern parallel. The Mammoth Steppe stretched from northern Spain across Europe and Asia to Alaska and the Yukon, the largest ecosystem on Earth at the time. It wasn't lush, but it was productive enough to support enormous herds of mammoths, horses, bison, woolly rhinos, saiga antelope, and other large herbivores. Population densities of these animals may have rivaled the Serengeti, except in a much colder climate. The vegetation was probably dominated by grasses, sedges, and hardy herbs, kept relatively short by constant grazing pressure, and it was maintained by the animals themselves. The megafauna, through their grazing, trampling, and fertilizing, kept the landscape open, preventing succession to tundra or forest. They were ecosystem engineers, and when they went extinct, the ecosystem they maintained collapsed. Without the grazing pressure, without the trampling, without the fertilization, the Mammoth Steppe transformed. In some areas, forests spread. In others, wet tundra replaced dry grassland. Today, no place on Earth resembles the Mammoth Steppe. It's an extinct ecosystem, vanished along with the animals that created and maintained it, leaving us only fossils and pollen records and the knowledge that the Ice Age world supported life in abundance in ways and places that seem impossible from our modern perspective. Beneath glaciers and ice sheets, hidden from view, water flows. Meltwater from the surface percolates down through cracks and crevasses. Geothermal heat from Earth's interior melts ice at the base. Friction from the glacier's movement generates heat. All this water has to go somewhere, and it carves channels beneath the ice, creating subglacial drainage systems that can be elaborate networks of tunnels and streams flowing through or under the glacier. These subglacial channels can be enormous, large enough to stand in, carved into the ice above and the bedrock below by the force of flowing water. As water accumulates, pressure builds, and sometimes, catastrophically, these drainage systems can't handle the volume. Water bursts out, releasing floods called glacial outburst floods, or jökulhlaups, an Icelandic term, because Iceland experiences these frequently. These floods can be staggeringly large, discharging more water than the Amazon River, briefly, as accumulated meltwater escapes all at once. Iceland has experienced numerous jökulhlaups, some of them devastating. Roads and bridges are washed away. Entire valleys are scoured. The floods carry enormous amounts of sediment and ice blocks the size of houses. The power is almost beyond comprehension. Natural forces operating at scales that dwarf human capabilities. And these aren't just historical events. They're ongoing. As glaciers thin and melt faster with climate warming, subglacial water systems are changing, potentially making outburst floods more frequent or more severe. The ice is still dangerous, still capable of releasing the forces it contains with sudden, overwhelming power. Around 13,000 years ago, as the Ice Age was ending and glaciers were retreating, a distinctive culture appeared across North America. We call them the Clovis people, named after the town in New Mexico where their characteristic stone tools were first identified. Clovis points, the spear points they made, are beautiful objects, carefully crafted with a distinctive fluting technique where a channel was flaked from the base, possibly to make hafting to a spear shaft easier. These points appear suddenly in the archaeological record and spread rapidly across North America, from Alaska to Mexico, from coast to coast. The Clovis people were hunter-gatherers, highly mobile, following herds of Ice Age megafauna. Their points have been found in association with mammoth and mastodon remains, suggesting they hunted these enormous animals. They lived during a unique time, a world in transition, where Ice Age megafauna still existed but were declining, where the climate was warming but hadn't yet stabilized, where landscapes were changing rapidly as ecosystems adjusted to new conditions. The Clovis culture lasted only a few hundred years before diversifying into various regional cultures with different tool technologies. But their brief fluorescence coincides almost exactly with the disappearance of North American megafauna around 11,000 years ago. Did Clovis hunters drive mammoths and other species to extinction? It's one of archaeology's most contentious debates. Some argue that skilled human hunters arriving in a landscape where animals had no experience with human predation could have caused rapid extinctions. Others point to climate change as the primary driver. Most likely, it was both. Clovis hunters adding pressure to populations already stressed by rapid environmental change, the combination proving fatal for species that had survived for millions of years. Where glaciers reach the ocean, they don't always just end. Sometimes they extend out over the water, forming floating platforms of ice called ice shelves. These aren't just thin sheets floating on the surface. They can be hundreds or even thousands of feet thick, enormous slabs of ice fed by glaciers flowing from land, floating on seawater but still connected to the glaciers behind them. Some ice shelves cover areas larger than entire countries. The Ross Ice Shelf in Antarctica is roughly the size of France. Ice shelves are important because they act as buttresses, holding back the glaciers behind them. The glaciers flow onto the ice shelf and spread out, and the ice shelf pushes back, creating resistance that slows the glacier's flow into the ocean. This buttressing effect helps stabilize ice sheets and control how fast ice flows from land into the sea. But ice shelves are vulnerable. They're already floating, so if they melt or collapse, it doesn't directly raise sea level. The ice was already displacing its weight in water. But when an ice shelf collapses, the glaciers behind it can accelerate dramatically. This has been observed repeatedly in recent decades. The Larsen B ice shelf in Antarctica collapsed in 2002, disintegrating in just a few weeks after existing for thousands of years. The glaciers that had been flowing into it suddenly lost their buttress and accelerated, flowing faster into the ocean, thinning, beginning to contribute to sea level rise. Ice shelves are the corks in the bottle, and as they weaken or disappear, they release the ice behind them. The Ice Age created these massive structures, and they've persisted through the entire Holocene. But now they're vulnerable, and their loss could accelerate the final retreat of Ice Age ice sheets that have survived for thousands of years. Some Ice Age animals survived into the modern era, persisting long enough for humans to photograph them, to study them, even to capture them in film. The thylacine, also called the Tasmanian tiger or Tasmanian wolf, was one of these tragic survivors. It was a marsupial predator, a carnivorous mammal that raised its young in a pouch, native to Australia, Tasmania, and New Guinea. It looked somewhat like a dog with tiger-like stripes across its back, though it wasn't closely related to either dogs or tigers. This was convergent evolution, a marsupial that had evolved to fill the ecological role of a medium-sized predator. Thylacines survived the megafauna extinctions that swept Australia around 45,000 years ago. They survived the end of the Ice Age. They survived for thousands of years alongside Aboriginal Australians. But they didn't survive European colonization, intensive hunting, bounties paid for dead thylacines, habitat loss, disease, and competition from introduced dogs led to their rapid decline. By the early 20th century, they were restricted to Tasmania. The last known thylacine died in Hobart Zoo on September 7, 1936, a female named Benjamin, though ironically it was actually female. There's footage of this individual, haunting film showing the animal pacing in its cage, yawning to reveal its remarkable gape. Thylacines outlived mammoths by over 10,000 years. They survived the Ice Age, survived dramatic climate changes, survived everything the Pleistocene threw at them. But they couldn't survive modern humans. It's a reminder that extinction isn't just an Ice Age phenomenon. We lost more species in the 20th century than at the end of the Ice Age in some regions. The thylacine survived everything the Ice Age world could throw at it, only to vanish in the modern era, in living memory, photographed and filmed but not saved. Earth's orbit around the Sun isn't a perfect circle. It's an ellipse, an oval shape, though a fairly subtle one. The difference between the farthest and closest points is only about 3%, but even this small variation matters for climate. And more importantly, the shape of the orbit changes over time. Sometimes the orbit is more circular, sometimes more elliptical, and this variation follows a predictable cycle lasting about 100,000 years. This is one of the Milankovitch cycles, and it appears to pace the major glacial-interglacial transitions. The eccentricity cycle affects how much seasonal variation Earth experiences. When the orbit is more elliptical, there's a bigger difference in the amount of solar radiation Earth receives when it's closest to the Sun versus farthest away. When the orbit is more circular, this seasonal variation is minimized. Combined with the precession cycle, which determines what season occurs when Earth is closest to the Sun, these orbital variations change the intensity of seasons in ways that affect ice sheet growth and melting. But here's the puzzle. The 100,000-year cycle is prominent in climate records from the past million years, but the actual forcing from orbital eccentricity at this timescale is quite weak. Something about Earth's climate system is amplifying this relatively small signal, turning subtle orbital variations into massive ice ages. Scientists think it involves feedbacks, carbon dioxide changes, ice albedo feedbacks, changes in ocean circulation, that amplify the initial orbital forcing. The orbit gives the nudge, but Earth's climate system does the heavy lifting, transforming that nudge into ice sheets miles thick. We still don't fully understand all the mechanisms, but the pattern is clear. Our orbit matters, and subtle changes in Earth's path through space can reshape the face of the planet. Stand in Manhattan today, surrounded by skyscrapers and crowds, and it's almost impossible to imagine that this entire island was once buried under ice. But during the last glacial maximum around 20,000 years ago, the Laurentide ice sheet extended far enough south to cover all of New York City. Manhattan, the Bronx, Brooklyn, Queens, all were beneath ice that was, in places, nearly 1,000 feet thick. You could have stood on top of that ice and been higher above sea level than many of the buildings that exist on Manhattan today. The ice didn't just cover the island, it shaped it. The bedrock beneath Manhattan is unusually hard and resistant to erosion, which is partly why it survived the grinding of the ice sheet, and also why it makes such a good foundation for skyscrapers. But the ice did leave its marks. It scoured and polished the bedrock, creating the smooth surfaces you can see in places where the rock is exposed. It deposited layers of glacial till, the unsorted mix of clay, sand, gravel, and boulders that now underlies much of the soil. Central Park contains numerous glacial erratics, boulders transported by the ice from locations sometimes hundreds of miles away, deposited when the ice melted. When the ice retreated around 18,000 years ago, it left behind a transformed landscape. The Hudson River, which had carved a deep valley before the ice came, was partly filled with glacial sediments. The entire geography of the region was reshaped, and the land, pressed down by the weight of ice, has been slowly rebounding ever since, rising millimeter by millimeter over thousands of years. The Manhattan we know is built on a foundation shaped by ice, on bedrock tested and toughened by glacial grinding, in a landscape still recovering from the last time ice ruled the world. Most Ice Age megafauna are gone, extinct vanished, known only from fossils and frozen remains. But a few survivors persist, living relics of a world that no longer exists. The musk ox is one of these survivors, a stocky, shaggy mammal that looks almost prehistoric, because in a sense it is. Musk oxen evolved during the Ice Age, perfectly adapted to Arctic conditions, and they've survived essentially unchanged while mammoths and woolly rhinos and cave bears all disappeared. Their adaptation to cold is extraordinary. Musk oxen have 2 layers of fur, a long outer coat of guard hairs that can reach nearly to the ground, and beneath that, an underlayer of incredibly fine wool called kiviut. This underlayer is one of the finest, warmest natural fibers known, about 8 times warmer than sheep's wool by weight. It's so fine and soft that it was once more valuable than cashmere. This insulation allows musk oxen to survive in some of the harshest environments on Earth, standing motionless through Arctic blizzards that would kill most other animals. They've also retained an Ice Age behavioral strategy. When threatened by predators, musk oxen form defensive circles, adults facing outward with their sharp horns, while calves shelter in the center. This strategy worked well against wolves and other Ice Age predators. Unfortunately, it makes them vulnerable to modern humans with guns, who can simply shoot the stationary circle of animals. But in remote Arctic regions where they still live, musk oxen persist, grazing on tundra vegetation, enduring brutal winters, using the same survival strategies their ancestors used when mammoths grazed alongside them. They're living fossils, Ice Age survivors still walking the earth, still using adaptations perfected hundreds of thousands of years ago. For most of human history, we were hunter-gatherers, following herds, collecting wild plants, moving with the seasons. Agriculture, the deliberate cultivation of crops and domestication of animals, is a relatively recent innovation, beginning only about 10,000 to 12,000 years ago. And the timing isn't coincidental. The Neolithic Revolution, as this transition to agriculture is called, happened as the Ice Age ended and the climate entered the stable, warm conditions of the Holocene. Why then? During the Ice Age, the climate was too unstable, too unpredictable for agriculture to succeed. Crops need reliable seasons, consistent rainfall, temperatures within certain ranges. The wild climate swings of the Ice Age, the Dansgaard-Oeschger events, the rapid shifts between cold and warm, would have made agriculture nearly impossible. But once the Holocene began around 11,700 years ago, the climate stabilized. Seasons became predictable. The same crops could be planted year after year with reasonable confidence they'd grow, and independently, in multiple locations around the world, the Fertile Crescent, China, Mesoamerica, the Andes, West Africa, humans began experimenting with cultivation. They domesticated wheat and barley, rice, maize, potatoes, millet. They domesticated sheep and goats, cattle and pigs. Within a few thousand years, most human societies had transitioned from mobile hunter-gatherers to sedentary farmers. This allowed permanent settlements, food surpluses, population growth, specialization of labor, and eventually cities, writing, and everything we think of as civilization. None of this would have been possible in the unstable climate of the Ice Age. The warm, stable Holocene gave us the environmental stability necessary for agriculture, and agriculture gave us civilization. Everything that followed, from the first cities to the internet, traces back to that transition, to the fortunate timing of the Ice Age ending and climate becoming hospitable for crops. Methane is a potent greenhouse gas, roughly 25 times more effective at trapping heat than carbon dioxide over a century-long time frame. During the Ice Age, methane was produced by microbes in wetlands, in ocean sediments, even within glaciers themselves, where microbial activity could occur in tiny pockets of liquid water within the ice. And under certain conditions of pressure and temperature, methane can become trapped in a cage-like structure of ice crystals, forming methane hydrate or methane clathrate, essentially methane frozen into ice. Significant deposits of methane hydrate exist in ocean sediments and in permafrost regions, and some exists within glaciers as well. These deposits are stable as long as temperature and pressure remain within certain ranges. But as the climate warms, as permafrost thaws and glaciers melt, this methane can be released. The ice cage breaks down, the methane escapes into the atmosphere, and because methane is itself a greenhouse gas, this creates a feedback loop. Warming releases methane, which causes more warming, which releases more methane. Scientists are concerned about this feedback, particularly in the Arctic, where permafrost is thawing rapidly. There are large deposits of methane hydrate locked in frozen ground and shallow ocean sediments that could potentially be released if warming continues. Some researchers worry about the possibility of a methane bomb, a rapid, large-scale release of methane that would dramatically accelerate warming. Others think the release will be more gradual, spread over centuries. Either way, the methane trapped in Ice Age permafrost and glaciers represents carbon that was removed from the atmosphere thousands of years ago, and its return could amplify the climate changes we're already experiencing, a final legacy of the Ice Age influencing the climate of the future. When we talk about Ice Age glaciation, we usually focus on the Northern Hemisphere, the massive ice sheets covering North America, Europe, and Asia. But the Southern Hemisphere had its own centers of glaciation, and one of the most significant was in Patagonia, the southern region of South America. The Patagonian ice sheet was enormous, covering much of southern Chile and Argentina, with ice flowing both east toward the Atlantic and west toward the Pacific. The mountains of the Andes provided ideal conditions for ice accumulation. High elevation, heavy precipitation from Pacific storms, cold temperatures. Ice built up in the mountains and flowed outward in massive glaciers, some of them extending far beyond the mountains into the lowlands. These glaciers carved the spectacular fjords of southern Chile, the deep channels and islands that characterize the coastline today. On the eastern side, glaciers advanced across the Patagonian steppe, depositing moraines that are still visible as ridges across the landscape. The Patagonian ice sheet was smaller than the Laurentide or Scandinavian ice sheets. It covered roughly 180,000 square miles at its maximum, compared to over 5 million square miles for the Laurentide. But it was still massive, and it had profound effects on South American climate and geography. Today, only remnants of this ice sheet survive. Glaciers in the Andes, ice fields like the southern Patagonian ice field, which is one of the largest expanses of ice outside Antarctica and Greenland. These remnants are melting rapidly, retreating at accelerating rates, losing mass to warming climate. The ice that once covered hundreds of thousands of square miles is shrinking to isolated pockets. the last fragments of Patagonia's ice age slowly disappearing. Cave bears earned their name honestly. They used caves extensively, particularly for hibernation. And they didn't just use them occasionally. Some caves in Europe show evidence of repeated, intensive use over thousands of years, with cave bears returning generation after generation to the same sites. The result is an extraordinary accumulation of bones. In some caves, the floor is literally paved with cave bear remains, skulls, jaws, long bones, vertebrae, layers upon layers of skeletons representing hundreds or thousands of individuals that died in these caves over millennia. Why so many deaths in hibernation sites? Hibernation is risky. Animals that hibernate must build up enough fat reserves to survive months without eating, and if they fail to gain enough weight, they may not survive the winter. Cave bears that died in caves likely starved during hibernation, their fat reserves exhausted before spring arrived. Young bears, old bears, sick bears, all were vulnerable. And in some years, if food was scarce during summer and autumn, many bears might enter hibernation without adequate reserves, leading to mass die-offs. The concentration of bones in certain caves suggests these sites were preferentially used, perhaps because they offered particularly good hibernation conditions, stable temperatures, protection from disturbance, suitable chamber sizes. Some caves show polish on the walls where bears rubbed against the rock for thousands of years, wearing grooves into solid stone. Cave floors contain layers of sediment mixed with bone fragments, churned by generations of bears digging dens, hibernating, dying, their remains gradually buried and preserved. These caves became unintentional crypts, repositories of cave bear bones that now provide paleontologists with unprecedented data about these Ice Age animals. Their age structure, health, diet, genetics, all preserved in the places where they came to sleep through Ice Age winters, and sometimes never woke. Earth doesn't spin perfectly upright as it orbits the sun. It's tilted, currently at about 23.5 degrees from vertical. This tilt is what gives us seasons. When the northern hemisphere tilts toward the sun, it experiences summer. 6 months later, when it tilts away, it experiences winter, but the amount of tilt isn't constant. Over a cycle of about 41,000 years, Earth's axial tilt oscillates between 22.1 and 24.5 degrees. It's a slow wobble, imperceptible on human timescales, but profound in its effects on climate. Greater tilt means more extreme seasons. When the tilt is at its maximum, summer gets more intense solar radiation, and winter gets less. The difference between summer and winter becomes more pronounced. When tilt is at its minimum, seasons are milder, cooler summers, warmer winters, and this matters enormously for ice ages. Ice sheets don't grow because winters get colder. They grow because summers aren't warm enough to melt the previous winter's snow. A reduction in summer intensity at high latitudes, even by just a degree or two, can allow snow to persist through summer, accumulate year after year, and eventually form glaciers. The 41,000-year obliquity cycle was actually the dominant driver of ice ages earlier in the Pleistocene, before the 100,000-year cycle took over about 1 million years ago. Climate records show strong 41,000-year variations in ice volume and temperature from that earlier period. Even now, the obliquity cycle contributes to climate variability, though it's overshadowed by the longer eccentricity cycle and by human influences on climate. But the tilt is still changing. still wobbling through its cycle, still exerting subtle influences on seasons and climate. A reminder that Earth's relationship with the sun is dynamic, always shifting, never quite settling into a stable configuration. At the head of a glacier, where it forms high in the mountains, there's often a distinctive feature called a bergschrund, a deep crack or crevasse that forms where the moving ice of the glacier pulls away from stationary ice or snow attached to the steep mountainside above. It's essentially the boundary between the glacier proper and the mountain, a gap that can be dozens of feet wide and hundreds of feet deep, revealing the internal structure of the glacier in cross-section. Looking into a bergschrund is like looking into a glacier's biography. You can see the layers, annual bands of snow compressed into ice, each layer representing 1 year's accumulation. You can see how the ice changes with depth, becoming denser and clearer as you go down, the air bubbles compressed out by the weight above. Sometimes you can see debris embedded in the ice, rocks and sediment picked up from the mountainside. And at the bottom, far below, you might glimpse the bedrock beneath, the solid mountain that the glacier sits on and slowly grinds away. Bergschrunds are dangerous places. Mountaineers who climb glaciated peaks must often cross them, and the crossing can be treacherous. A jump across a gap over a bottomless crack, or a careful descent into the crevasse and climb out the other side. The ice around bergschrunds is often unstable, shifting and calving as the glacier moves. But they're also scientifically valuable, providing access to the interior of glaciers without the need for drilling, offering glimpses of the structure and composition of ice that would otherwise remain hidden beneath the glacier's surface. Ice cores don't just preserve carbon dioxide and methane. They also contain trace amounts of other atmospheric compounds, including organic acids like acetic acid, the same compound that gives vinegar its sharp smell and taste. Acetic acid in the atmosphere comes from various sources: plant decay, biomass burning from forest fires, even emissions from vegetation. It gets incorporated into snow and ice, and once frozen, it's preserved, sometimes for hundreds of thousands of years. By measuring the concentration of acetic acid and other organic compounds in different layers of ice cores, scientists can learn about past vegetation patterns and fire activity. High levels of acetic acid might indicate periods when forests were extensive or when forest fires were particularly common. Low levels might suggest less vegetation or fewer fires, perhaps during cold, dry glacial periods when tree cover was reduced. It's a form of chemical archaeology, reading the composition of ancient atmosphere to understand what was happening on Earth's surface when that snow fell. The fact that such delicate reactive compounds can survive, preserved in ice for so long, is remarkable. Acetic acid is fairly volatile. It should evaporate or react with other chemicals. But frozen in ice, isolated from the atmosphere, protected from UV radiation and microbial activity, it persists. Each molecule of acetic acid in an ice core is a messenger from the past, possibly produced by a forest fire that burned during the Ice Age, carried into the atmosphere, deposited with snowfall, and sealed away in ice until scientists extracted and measured it tens of thousands of years later, reconstructing ancient environments from chemical traces preserved in frozen time. The end of the Ice Age brought extinctions, but they didn't all happen at once globally. Instead, Megafauna extinctions occurred at different times on different continents, following a pattern that strongly correlates with human arrival. Australia lost its megafauna earliest, around 45,000 to 50,000 years ago. Giant wombats, marsupial lions, enormous kangaroos, all disappearing within a few thousand years of the first human colonization. Eurasia's extinctions were more gradual, stretched over tens of thousands of years as humans spread and populations grew. The Americas saw perhaps the most dramatic extinctions, concentrated in a narrow window around 11,000 to 13,000 years ago. Within just a few thousand years, North America lost mammoths, mastodons, horses, camels, saber-toothed cats, giant ground sloths, short-faced bears, and many more species, over 30 genera of large mammals gone. South America's losses were even more severe. Madagascar lost its megafauna only about 2,000 years ago, when humans finally arrived on the island. New Zealand lost its giant moa birds within a few hundred years of Polynesian settlement, around 1300 CE. This pattern, extinctions shortly following human arrival, suggests that humans played a significant role, though climate change was certainly also a factor. The debate continues about the relative importance of hunting versus climate, but the correlation between human arrival and extinction is striking. It appears that Ice Age megafauna, which had survived for millions of years through multiple climate cycles, couldn't survive the combination of rapid climate change and a new, highly effective predator. Humans with sophisticated hunting strategies, tools, and perhaps most importantly, no instinctive fear response from prey animals that had never encountered human hunters before. Glaciers move, but usually that movement is slow, steady, continuous, a gradual flow measured in feet per day or less. But sometimes glaciers lurch. A large section of ice suddenly accelerates, sliding forward rapidly over the bedrock or over a layer of water at the base. This sudden movement generates seismic waves, vibrations that travel through the earth and can be detected by earthquake monitoring stations thousands of miles away. These are glacial earthquakes, and they're becoming more common as glaciers thin and destabilize with climate warming. Glacial earthquakes don't feel like tectonic earthquakes. You wouldn't notice one if you were standing near the glacier. The shaking is subtle, the frequency is different, the duration is longer. But seismometers can detect them, and by analyzing the seismic signals, scientists can determine where the earthquake occurred, how large the ice displacement was, even how fast the ice moved. It's a way of monitoring glacier dynamics remotely, using the vibrations the glaciers themselves produce. What's alarming is that glacial earthquakes in Greenland have increased dramatically over the past few decades. In the 1990s, there were perhaps a few dozen detected per year. By the 2010s, there were hundreds. This increase corresponds to accelerating ice loss, to glaciers flowing faster, to ice sheets becoming less stable. Each glacial earthquake is evidence of ice in motion, of glaciers responding dynamically to warming, of ice age remnants beginning to move faster than they have in thousands of years. The earth is literally shaking with the movement of melting ice, and the seismometers are recording the ice age's accelerating retreat. Earth wobbles as it spins like a top winding down, though on a time scale of about 23,000 years per complete wobble. This wobble means that the direction Earth's axis points changes slowly over time. Currently, the North Pole points roughly toward Polaris, the North Star. But 13,000 years ago, it pointed toward a different star, and 13,000 years from now, it will point toward yet another star. This is called axial precession, or the precession of the equinoxes. Precession has important climate effects because it changes when, during Earth's orbit, each hemisphere experiences summer and winter. Currently, Earth is closest to the Sun in early January, during Northern Hemisphere winter. This means northern winters are slightly milder than they would be otherwise, and northern summers are slightly cooler because Earth is farthest from the Sun during northern summer. But in about 11,000 years, precession will have shifted things so that Earth is closest to the Sun during northern summer. This will make northern summers more intense and northern winters colder, more extreme seasons in the northern hemisphere. Why does this matter for ice ages? Because ice sheets form in the northern hemisphere, where there's more land at high latitudes, and they're sensitive to summer temperatures. Cooler summers mean more snow persists through summer, allowing ice sheets to grow. So when precession aligns with other orbital cycles to produce particularly cool northern summers, glaciation is favored. When it produces warmer summers, ice sheets melt. Precession is one of the key cycles in the Milankovitch theory, a slow wobble that helps pace the advance and retreat of ice ages, determining whether ice accumulates or melts based on nothing more than which direction Earth happens to be pointing as it orbits the Sun. Hibernation is an impressive adaptation, lowering metabolism, slowing heart rate and breathing, sleeping through months of harsh winter. But some Ice Age animals took hibernation to an extreme that seems almost impossible. The Arctic ground squirrel, which still exists today as a living relic of Ice Age fauna, can lower its body temperature below the freezing point of water during hibernation. Its body temperature can drop to as low as 2.9 degree Celsius, about 27 degree Celsius, below the temperature at which water normally freezes. How is this possible without the animal freezing solid and dying? The blood and tissues become supercooled, cooled below freezing point while remaining liquid. This requires special adaptations. The animal's cells produce cryoprotectants, chemicals that lower the freezing point of cellular fluids and prevent ice crystal formation. The metabolism doesn't stop completely, but it slows to an almost imperceptible level, just enough to keep cells alive and prevent ice from nucleating. Every few weeks during hibernation, the squirrel warms up briefly, raising its body temperature back to normal for a few hours before cooling down again. This extreme hibernation allows Arctic ground squirrels to survive in some of the harshest environments on Earth. Enduring Arctic winters in burrows beneath the snow where temperatures can plummet far below freezing. Their Ice Age ancestors likely used the same strategy, perhaps even in more extreme forms when glacial periods brought even colder conditions. It's a reminder that Ice Age animals developed extraordinary adaptations to cold, pushing the boundaries of what mammalian physiology can achieve. And some of those adaptations persist in the descendants that still survive today, still employing biochemical tricks we don't fully understand to endure conditions that would kill most other warm-blooded animals. At the bottom of glacial lakes, sediment accumulates in distinctive patterns. During summer, when meltwater is flowing rapidly from glaciers, coarser sediment, sand and silt, gets carried into the lake and settles out. During winter, when melting slows or stops and the lake surface freezes, only the finest clay particles settle, creating a thin, dark layer. This creates paired layers called varves, a light, coarse summer layer, and a dark, fine winter layer. Each pair represents 1 year, like tree rings, but made of sediment. Varves are extraordinarily useful for dating. You can count them backward in time, layer by layer, establishing precise chronologies. In lakes where deposition has been continuous and undisturbed, varve sequences can extend back thousands of years. Swedish varve chronologies, for instance, cover about 13,000 years of post-glacial time with annual precision, and within each varve, the thickness and composition tell you something about climate that year. Thick summer layers indicate lots of meltwater and sediment input, possibly a warm summer. Thin layers might indicate cooler conditions, less melting, less sediment transport. By analyzing varves from multiple lakes and correlating them with ice cores and other climate records, scientists can reconstruct past climate variations with remarkable precision and resolution. They can identify individual years when volcanic eruptions deposited ash layers across wide regions. They can detect the Younger Dryas cooling event and see exactly how quickly it started and ended. Varves are annual pages in a sedimentary book, each one recording the seasonal rhythm of glacial lakes that existed thousands of years ago, preserving information about Ice Age climate with a temporal resolution measured in single years rather than centuries or millennia. Most ice core records come from polar regions, Antarctica and Greenland, where ice is thick and ancient. But ice caps also exist in tropical mountains, sitting at high enough elevations that they remain frozen year-round, despite being near the equator. These tropical ice caps are much thinner and younger than polar ice sheets, but they're scientifically valuable because they record climate in regions where few other long-term archives exist. The Huascarán ice cap in Peru, sitting atop a mountain at over 20,000 feet elevation, has provided one of the most important tropical ice core records. The Huascarán ice core, drilled in the 1990s, contains ice spanning about 18,000 years, back to near the last glacial maximum. This ice preserves a detailed record of tropical South American climate, showing temperature changes, precipitation patterns, atmospheric dust content, and even evidence of Amazon forest fires in the form of soot particles. It revealed that tropical regions experienced significant cooling during the Ice Age, about 5 to 6 degrees C colder than today, and that the Younger Dryas cooling event, which so dramatically affected the northern hemisphere, was also felt in the tropics. But tropical ice cores are endangered. As the climate warms, these ice caps are melting rapidly. The Huascarán ice cap has lost thickness and area significantly since the ice core was drilled. Other tropical ice caps on Kilimanjaro, in the Andes, in New Guinea, are disappearing entirely. The ice that took thousands of years to accumulate is melting away in decades, and with it, the climate records it contains. Scientists are racing to drill cores and extract data before the ice is gone forever, before the archive melts and flows away, taking irreplaceable information about tropical climate history with it. When ice sheets grow, they press the crust down. When they melt, the crust rebounds upward. But this isn't a simple, localized effect. The mantle beneath the crust is a thick, viscous fluid, and when you push down in one place, you create a bulge somewhere else, like pushing down on a waterbed. During the Ice Age, the weight of ice sheets depressed the crust in glaciated regions, but it also created a peripheral bulge around the edges of the ice sheets, where the displaced mantle material pushed the crust upward. Now, thousands of years after the ice melted, the crust is still adjusting. Formerly glaciated regions are still rising: Scandinavia, Canada, northern Scotland. But the peripheral areas that were bulged upward during the Ice Age are now sinking. Coastlines that were higher during the Ice Age are subsiding. This is happening along the U.S. Atlantic coast, contributing to higher rates of relative sea level rise in places like Chesapeake Bay and the mid-Atlantic states. The land is sinking and the ocean is rising, creating particularly rapid changes in coastal elevation. This glacial isostatic adjustment complicates our understanding of sea level change. When you measure sea level at a tide gauge or with satellites, you're measuring the combined effect of ocean water volume changes and vertical land movement. In some places, land is rising faster than sea level, making relative sea level fall. In others, land is sinking, amplifying sea level rise. To understand global sea level change accurately, you have to account for these vertical land movements, which are still ongoing responses to Ice Age ice sheets that disappeared 10,000 years ago. The ice is gone, but the Earth's crust is still adjusting, still bouncing back from the weight that once pressed it down, a slow rebound that will continue for thousands of years more. Antarctica wasn't always the isolated, frozen continent it is today. 50 million years ago, it was still connected to South America and Australia, part of the ancient supercontinent Gondwana that was slowly breaking apart. But around 34 million years ago, something crucial happened. The Drake Passage between Antarctica and South America widened enough to allow ocean currents to flow unimpeded around the entire continent. This created the Antarctic Circumpolar Current, the most powerful ocean current on Earth, circulating clockwise around Antarctica and effectively isolating it from warmer ocean waters to the north. This isolation had profound consequences. Before the current established, warm water from the tropics could reach Antarctica, moderating its climate. But once the Antarctic Circumpolar Current formed, it created a barrier, a wall of cold water that prevented warm currents from reaching the continent. Antarctica began to cool. Snow that had melted in summer began to persist. Ice accumulated. Within a few million years, the entire continent was covered in ice, transforming from a green, forested land to the frozen wilderness we know today. The Antarctic Circumpolar Current still flows today, driven by the powerful westerly winds that circle the Southern Ocean. It's the engine of Southern Hemisphere ocean circulation, connecting the Atlantic, Pacific, and Indian Oceans, distributing nutrients and heat and carbon dioxide. And it continues to isolate Antarctica, maintaining the continent's frozen state. Some scientists worry that if the current weakens due to climate change, warmer water might reach Antarctica more easily, accelerating ice melt. The current that froze Antarctica might also be the key to keeping it frozen or not, depending on how the climate system evolves in the coming centuries. The Ice Age wasn't uniformly frozen. Even in Alaska, which was partially covered by glaciers and ice sheets, there were pockets of land that remained ice-free, refugia where plants and animals could survive when conditions everywhere else were too harsh. Some of these refugia existed because of unique local geography: south-facing slopes that received more sunlight, valleys sheltered from the worst winds, areas near the coast where ocean currents moderated temperatures. Others might have been maintained by geothermal heat from volcanic activity or hot springs. In these refugia, trees and shrubs survived far north of their normal Ice Age range. Pollen records show that spruce, birch, and other tree species persisted in small pockets in Alaska, even during full glacial conditions when similar latitudes in Europe and Asia were treeless tundra. These refugia served as reservoirs of biodiversity, preserving species through the worst of the Ice Age and allowing them to rapidly recolonize when conditions improved. The genetic signatures of these refugia are still detectable today in modern plant populations. By analyzing DNA from trees across Alaska and comparing genetic diversity in different regions, scientists can identify areas that likely served as refugia. They show higher genetic diversity and contain unique genetic lineages not found elsewhere. It's a bit like detective work, using molecular evidence to identify safe harbors that existed thousands of years ago. Invisible in the landscape now, but recorded in the genes of the organisms that sheltered there when ice covered most of the surrounding territory. Geologists divide Earth's history into time periods, eons, eras, periods, epochs, based on significant changes in the rock record, in fossils, in climate. The boundary between the Pleistocene epoch and the Holocene epoch, the period we live in now, is defined by the end of the last glacial period, set at 11,700 years ago. This isn't an arbitrary date. It marks a genuine transition, a shift from the unstable, cold climate of the Ice Age to the warm, stable climate that has characterized the past 11,700 years. This stability has been extraordinary. Compared to the wild climate swings of the Pleistocene, the Dansgaard-Oeschger events, the Younger Dryas, the repeated glacial-interglacial cycles, the Holocene has been remarkably stable. Temperatures have varied by only a degree or two globally. There have been no dramatic ice sheet advances, no massive megafauna extinctions, no climate shifts anywhere near as severe as those common during the Pleistocene. This stability is what allowed human civilization to flourish. Agriculture requires predictable seasons, stable rainfall patterns, climates that don't shift dramatically within a human lifetime. Cities require confidence that the same location will remain habitable for generations. The Holocene provided these conditions, but there's increasing discussion about whether we should define a new epoch, the Anthropocene, to mark the period when human activities began to significantly alter Earth's geology and climate. If we do, the Holocene would be recognized as a brief, stable interlude between the chaotic Ice Age and whatever comes next. A fortunate window of climatic calm that lasted just long enough for our species to build everything we think of as civilization. The Holocene epoch officially is still ongoing, but many scientists argue that we've entered a new geological epoch defined by human influence on Earth's systems, the Anthropocene, the age of humans. The proposed starting date varies depending on who you ask. Some suggest it began with the Industrial Revolution, when fossil fuel burning began to significantly alter atmospheric composition. Others point to the mid-20th century and the Great Acceleration, when population growth, nuclear testing, plastic production, and ecological changes all skyrocketed. The evidence for human impact is overwhelming. Atmospheric carbon dioxide is higher than any time in at least 800,000 years, and it's rising faster than any natural change in the ice core record. We've moved more sediment and rock through mining and construction than all the world's rivers combined. We've spread novel materials, plastics, concrete, radioactive isotopes from nuclear testing across the planet in layers that will be detectable in the geological record for millions of years. We've caused extinction rates that rival the great mass extinctions of the past. We've altered the nitrogen and phosphorus cycles, changed the chemistry of the oceans, modified ecosystems globally. And we may be preventing the next ice age. Based on orbital cycles, the Earth should be slowly heading toward the next glaciation, expected to begin in perhaps 50,000 years. But human-caused warming may prevent this from happening. We've added so much carbon dioxide to the atmosphere that it might delay the next ice age by 100,000 years or more, or possibly prevent it entirely. We've become a geological force, powerful enough to override the orbital cycles that have paced ice ages for millions of years, rewriting the script of Earth's climate future in ways we're only beginning to understand. The Drake Passage is notorious among sailors as the roughest, most treacherous ocean crossing on Earth. Located between Cape Horn at the southern tip of South America and the South Shetland Islands of Antarctica, it's about 500 miles wide at its narrowest point, and the water there is almost constantly turbulent. Waves can reach 40 feet or higher. Winds scream across the surface. The Antarctic circumpolar current funnels through the passage, and there's no land to slow it down or moderate the weather. Ships pitch and roll dramatically, and even modern vessels equipped with stabilizers struggle in Drake Passage conditions. But this fearsome passage is geologically young. It opened only about 34 million years ago when South America and Antarctica, once connected, finally separated completely as tectonic plates continued to drift apart. Before the Drake Passage opened, ocean currents couldn't flow all the way around Antarctica. Warm water from lower latitudes could reach the Antarctic coast, keeping temperatures moderate. But once the passage opened, everything changed. The Antarctic circumpolar current established itself, isolating Antarctica, and the continent began its transformation into the frozen wilderness it is today. The opening of the Drake Passage was one of the most consequential geological events in recent Earth history. It didn't just create a rough ocean crossing. It fundamentally reorganized global ocean circulation, triggered the freezing of an entire continent, likely contributed to global cooling, and helped set the stage for the ice age cycles that would dominate the past few million years. A gap in geography, a separation of land masses, and the climate of the entire planet shifted in response. It's a reminder of how connected everything is, how changes in one part of the world can cascade through the Earth system in unexpected ways. When glaciers melt, they don't just disappear cleanly, leaving bare rock behind. They deposit their load, everything they've been carrying, from the finest clay particles to boulders the size of houses, in a jumbled, unsorted mess called glacial till. Unlike sediment deposited by water, which sorts itself by size, heavy particles settling first, fine particles carried farther, glacial till is chaotic. Clay, sand, gravel, and boulders all mixed together with no organization, no layering, just dropped wherever the ice happened to melt. Vast areas of the northern hemisphere are covered in glacial till deposited when the last ice sheets melted. Much of Canada, the northern United States, northern Europe, and Russia sit on top of thick deposits of till. This till creates distinctive landscapes, gently rolling hills, irregular topography, poor drainage leading to numerous lakes and wetlands. The till is often fertile, containing minerals ground from many different rock types and mixed together, which is why some of the world's most productive agricultural regions are on glacial till. But till can also be challenging. It's poorly sorted, meaning it has a wide range of particle sizes, which affects how water moves through it and how suitable it is for construction or agriculture. Building foundations sometimes encounter unexpected boulders embedded in otherwise fine sediment. Digging wells can be complicated when you don't know if you'll hit clay, sand, gravel, or solid rock. Glacial till is the messy legacy of Ice Age glaciers, an unsorted archive of everything the ice carried, now covering millions of square miles and forming the foundation of landscapes where millions of people live, often without realizing they're living on the debris left behind by glaciers that melted 10,000 years ago. The Holocene is supposed to be stable, a warm interglacial with relatively consistent climate, and it has been compared to the Pleistocene. But it hasn't been perfectly stable. About 200 years ago, there was a sudden cooling event that shows up in climate records from around the world, the 8.2 kiloyear event, named for its timing approximately 200 years before present. In some regions, temperatures dropped by several degrees for a century or two before recovering. In Greenland, the cooling was particularly pronounced, showing up clearly in ice cores. What caused it? The most likely explanation is the catastrophic drainage of glacial Lake Agassiz. This enormous lake in North America had been dammed by remnants of the retreating ice sheet. But around 8,200 years ago, the ice dam failed, or the lake found a new outlet to the north. An enormous volume of fresh water, possibly equivalent to all the water in all the Great Lakes, suddenly poured into the North Atlantic and Arctic Oceans. This flood of fresh water disrupted the Atlantic meridional overturning circulation, weakening the ocean conveyor belt that transports heat northward. With less heat transport, the northern hemisphere cooled. The cooling was significant but brief, lasting perhaps a century or two before ocean circulation recovered and temperatures rebounded. But it's a reminder that even during the stable Holocene, climate can shift abruptly. The collapse of Ice Age remnants, glacial lakes draining, ice sheets retreating, had the power to perturb global climate even thousands of years after the Ice Age officially ended. And it's a warning about potential future disruptions. If the Greenland ice sheet were to melt rapidly, pouring enormous volumes of fresh water into the North Atlantic, it could potentially weaken ocean circulation and trigger regional cooling, even as the planet warms overall, creating complex and unexpected climate patterns. One of the most important discoveries from ice core research is the tight correlation between atmospheric carbon dioxide and temperature over the past 800,000 years. When scientists plot CO2 concentration from ice core bubbles against temperature reconstructed from ice isotopes, the two curves track each other almost perfectly through multiple glacial interglacial cycles. When temperature rises, CO2 rises. When temperature falls, CO2 falls. They move together in synchrony, like two dancers perfectly matched. This raises an interesting question: which leads and which follows? In natural glacial cycles, orbital changes appear to trigger the initial warming or cooling, and then CO2 responds, amplifying the temperature change. So temperature leads slightly, and CO2 follows. But then the CO2 amplifies the warming or cooling, creating a feedback loop. It's not a simple cause and effect, but a complex interaction where changes in one reinforce changes in the other. What's unprecedented about the present is both the level and the rate of CO2 increase. Current CO2 levels around 420 parts per million are higher than any point in the 800,000-year ice core record, higher than any previous interglacial warm period. And the rate of increase is faster than any natural change preserved in ice cores. In the past, CO2 rose by perhaps 80 parts per million over thousands of years during glacial-interglacial transitions. We've increased it by over 140 parts per million in less than 2 centuries. The ice cores give us context and baseline, showing us what's normal variability over hundreds of thousands of years. And they make clear that what's happening now is extraordinary, outside the bounds of natural variability, a human-caused perturbation to a system that has operated within relatively stable bounds for nearly 1 million years. This is one of the enduring mysteries of Ice Age research. The 100,000-year cycle of glacial-interglacial oscillations is clearly visible in climate records from the past 1 million years. Ice sheets grow for about 90,000 years, reaching maximum extent, then collapse relatively quickly over about 10,000 years, and the cycle repeats. The pattern is remarkably regular. But here's the puzzle. The orbital forcing that drives ice ages, the Milankovitch cycles, has only a very weak component at 100,000 years, corresponding to changes in orbital eccentricity. The eccentricity cycle is real, and it does affect how much seasonal variation in solar radiation Earth experiences. But the actual forcing is quite small, too small to explain the magnitude of Ice Age cycles on its own. Somehow the Earth's climate system is amplifying this weak 100,000-year signal, turning subtle orbital variations into massive ice sheets and dramatic climate changes. But we don't fully understand the amplification mechanisms. Various hypotheses have been proposed. Perhaps it's related to ice sheet dynamics. Ice sheets might have natural growth and collapse cycles that happen to resonate with the orbital forcing. Perhaps it involves carbon dioxide feedbacks, with CO2 being drawn down during glacial periods and released during deglaciations, amplifying temperature changes. Perhaps it's related to ocean circulation changes, or to interactions between different ice sheets, or to complex feedbacks we haven't identified yet. Most likely, it's some combination of all these factors, but the fact remains. We can describe the 100,000-year cycle in detail. We can measure it precisely in ice cores and sediment records, but we can't completely explain why it's the dominant rhythm. There's still mystery in the Ice Age, still questions that remain unanswered, still mechanisms we're working to understand. Ice ages are not permanent. They come, they reshape the world, and they go. For millions of years, they've cycled in rhythm with orbital changes, each glaciation carving valleys and moving mountains, each deglaciation flooding coastlands and creating new landscapes. Every ice age leaves its mark, in the valleys carved by glaciers, in the moraines deposited by retreating ice, in the species that evolved to survive the cold, or the species that went extinct because they couldn't adapt. The Ice Age that ended 11,700 years ago transformed Earth profoundly. It created the Great Lakes and the fjords of Norway and the rolling hills of New England. It drove mammoths and saber-toothed cats and cave bears to extinction, while allowing humans and wolves, and ravens to survive. It lowered sea levels and exposed land bridges, allowing humans to spread across the globe, reaching every continent except Antarctica. And when it ended, when the ice melted and sea levels rose, and forests spread across formerly frozen lands, it created the conditions for agriculture and civilization, for the entire human world we know today. We live in the pause between ice ages, in an interglacial that may end naturally in tens of thousands of years, or may be extended indefinitely by human influences on climate. The Ice Age shaped us, our evolution, our migrations, our adaptations. And in a sense, we're still children of the Ice Age, products of a world that cycled between freeze and thaw, adapted to change, resilient in the face of environmental extremes. The ice will come again someday, perhaps, or perhaps we've changed the rules enough that it won't. Either way, the Ice Age isn't just history. It's written into the landscape we inhabit, into the genes of every organism that survived, into the very air we breathe. The ice may be gone, but its legacy surrounds us, invisible and permanent, a reminder that the earth is always changing, always in motion, always becoming something new. And so we've journeyed through 100 facts about the Ice Age, through frozen worlds and vanished creatures, through climate cycles measured in millennia and orbital wobbles that remake the planet. We've stood beneath ice sheets miles thick, walked with mammoths across grasslands that no longer exist, watched glaciers carve valleys and flood continents, seen species disappear and others endure. The Ice Age isn't distant history, safely locked in the past. It's recent, it's present. It surrounds us in the shape of every valley, the distribution of every species, the composition of the air we breathe. We are Ice Age survivors, all of us, descendants of the organisms that endured through climate chaos and megafauna extinctions, and landscapes transformed beyond recognition. And the Ice Age may not be finished with us yet, but for tonight, that's enough. You've learned, you've traveled through time, and perhaps you're ready to rest, to let these facts settle gently in your mind like snow, accumulating on a mountain, layer by layer, building something that will persist. Thank you for listening. Thank you for your curiosity. And thank you for being here, for sharing this quiet exploration of our planet's frozen past and uncertain future. Sleep well. Dream of ice, if you like, or of green Saharas and mammoth steppes, of worlds that were and worlds that might yet be. The Ice Age waits in the geological record, patient and permanent, ready to share its stories whenever you return. Good night.